Hello there, and welcome to Life Beyond Seen, where curiosity slows down long enough to take a deep breath and wander somewhere extraordinary. Tonight's quiet journey drifts far from cities, oceans and stars. It drifts to the very bottom of our planet, where sunlight never reaches and the air turns into something sharp enough to sting. It's a place most of us will never see, and even the bravest scientists can only touch through cables and data. But it's real, and it's vast, and it's hiding something that might change how we think about life itself. Beneath the South Pole's glaciers lies a world sealed away for millions of years, a dark ocean of pressure and silence. And yet, despite our satellites and drills and restless curiosity, we can't truly explore it. Not completely. Not yet. Maybe not ever. Before we sink into that frozen stillness, I'd like to ask something simple. Where in the world are you listening from tonight? Maybe it's late where you are and your room is dim and there's a small hum in the background that keeps you anchored to now. Maybe it's morning and the day is beginning to unfold in slow motion. Wherever you are, imagine for a moment that beneath your feet, far, far beneath, is a continent of ice 2 miles thick. And under that ice is an entire landscape no one has walked on. Rivers, valleys, mountains, lakes, all hidden away under a frozen ceiling. It's one of the last truly unreachable frontiers left on Earth. If you find this kind of calm curiosity comforting, if it helps your thoughts slow down for a while, it would mean a lot if you liked this video or subscribed. It helps this small, quiet corner of science reach someone else who might be lying awake wondering about the same things. And now, let's begin to sink under the ice slowly, carefully, following the faint traces of heat and sound that reveal what our eyes never could. Most of what we know about the Antarctic interior doesn't come from seeing it. It comes from listening, bouncing radio waves through ice, or reading tiny changes in gravity from satellites that orbit far above. What those instruments tell us is both fascinating and frustrating. Beneath that frozen sheet, there are mountains as tall as the Alps, rivers that never freeze, and valleys so deep they could swallow entire cities. The Antarctic ice sheet isn't just ice, it's a continent's worth of geology buried under a frozen ocean. The ice itself is more like a slow-moving glacier sea, grinding over rock, reshaping it, sealing away anything that might once have lived there. When scientists talk about exploring beneath the South Pole's glaciers, they're talking about working at the limit of what humans can endure. Temperatures drop below minus 70 degrees Celsius. Winds can strip equipment bare in hours. Even standing on the surface is like being on another planet. And yet the real mystery lies not at the surface but miles below. Down there, under millions of years of compressed snow, are vast lakes and water systems that have been sealed away from the atmosphere since before humans existed. The most famous of these hidden reservoirs is Lake Vostok. It's roughly the size of Lake Ontario, but it sits beneath nearly 4 kilometers of ice. Its water hasn't seen the sky in maybe 15 million years. To reach it safely, without contaminating it with modern bacteria or chemicals, is one of the hardest scientific challenges ever attempted. Imagine trying to touch something ancient without leaving a fingerprint. That's what scientists face every time they plan to drill through Antarctic ice. The risk isn't just mechanical, it's moral. If they breach a sealed ecosystem, even a single drop of modern oil or microbe could destroy data that nature has been guarding for eons. This is why exploration under the glaciers moves so slowly, so cautiously, so painfully carefully. Every motion must be clean, every instrument sterilized, every sensor monitored. Even the smallest mistake could ruin the one chance to understand what lies beneath. It might sound excessive, but there's a reason for this almost obsessive caution. We've learned the hard way that life, when it exists, finds ways to survive where it shouldn't. On the surface of Mars, in the acidic lakes of Tanzania, deep inside nuclear reactors, microbes have been found thriving in conditions that should kill everything. So if we do find life under Antarctica's glaciers, life that's adapted to total darkness, crushing pressure, and isolation. It could tell us what life might look like on Europa or Enceladus, the icy moons orbiting Jupiter and Saturn. In a sense, Antarctica is a test lab for the cosmos, and that's why we treat it like sacred ground. But before those ideas of extraterrestrial parallels and biochemistry spark too brightly, it helps to picture what this hidden world is actually like. Beneath the ice is no clear cavern or open tunnel. It's not a frozen cave with glittering walls or some mythic kingdom of frost. It's a crushing labyrinth of solid ice, laced with thin layers of liquid water that move so slowly they might as well be sleeping. In some areas, the ice presses against the rock below with hundreds of tons of pressure per square metre. The temperature there hovers just below freezing, warmed only by the faint heat of the Earth's core. Where the ice is thinner, it clings to rock. Where it's thicker, it flows outward, dragging stone and sediment like a slow avalanche frozen in time. For most of history, no one knew this world existed. Early explorers saw only the surface, endless white plains, ridges, storms that erased footprints in seconds. They thought the continent beneath might be flat or even oceanic. It wasn't until the middle of the 20th century, when scientists began bouncing radar signals through ice, that we started to glimpse the hidden terrain. What they found was astonishing. Beneath East Antarctica lay a landscape of buried mountain ranges, the Gamburtsev Subglacial Mountains, stretching hundreds of kilometres long. Beneath West Antarctica, a patchwork of basins and ridges carved by ancient rivers, now reversed and buried. Between them, sealed lakes, some connected by rivers of meltwater, others isolated for epochs. The picture that emerged was of a living continent locked in ice, and yet, for all the wonder, we still can't reach most of it. The reasons are as much practical as they are philosophical. Technology that can survive the cold, the pressure, and the contamination requirements is expensive and fragile. Drills that can melt or bore through miles of ice need to remain sterile all the way down, and that means everything, from the water used for drilling to the cables feeding power, must be kept pure. One particle of dust, one trace of fuel, could invalidate years of preparation. There's also the problem of distance. The South Pole is one of the most remote places on Earth. Getting equipment there involves massive logistics, icebreakers, cargo planes, overland convoys through snowfields that shift every year. The cost of a single deep ice mission can reach tens of millions of dollars, and the payoff might be a few milliliters of water that took decades to reach. Still, scientists try. They send probes through boreholes as narrow as a handspan, each one sterilized, each descent a slow, silent negotiation with ice that could crush metal. Some of those probes never return. They get trapped or frozen in place as the borehole refreezes behind them. The ice doesn't forgive mistakes. It moves, flows, closes over intrusions. To explore under Antarctica's glaciers is to work against an opponent that is both patient and absolute. Even if we could freely drill into those subglacial lakes, we'd still face another problem. What if what's down there is alive? Not in the way we think of life on the surface, with plants and animals, but in microscopic communities that have evolved in total isolation. Any contamination could not only harm them but destroy our ability to know what they truly are. That's why researchers treat every drop of subglacial water as both treasure and responsibility. They sample indirectly, using meltwater that seeps upward naturally, or they analyse the chemistry of refrozen ice cores taken from above. These methods give hints, trace DNA, unusual gases, chemical signatures, but not a full picture. The real world beneath remains beyond reach, a mystery seen only through data. What makes this frontier even more intriguing is that it isn't static. The base of the Antarctic ice sheet moves. It flows, slowly but surely, like syrup under unimaginable weight. Some areas slip over the rock at several meters per year, others barely move. Beneath those shifting layers, water channels form and collapse, lakes drain and refill, the continent breathes on geological time, a slow rhythm we can only measure, not feel. And because it changes, any direct exploration risks disrupting a system that's still alive in its own frozen way. There's also a human element to all this, a sense of humility. For generations, humans have prided themselves on mapping the world, climbing every peak, diving every trench. Antarctica resists that impulse. It remains largely unmapped beneath its ice. Even our best satellite maps have blind spots, places where radar can't penetrate, or where the ice is too thick for echoes to return. In those dark zones, we rely on models and educated guesses. To some, that's frustrating. To others, it's comforting. There's something beautiful about knowing that even in the 21st century, a piece of Earth still hides its secrets completely. When we imagine exploration, we picture movement, people crossing distances, machines drilling, samples rising to the surface. But in Antarctica, exploration often means stillness. It means waiting for signals, listening for the faintest changes in echo or magnetism. It means acknowledging that the act of not touching can be more powerful than the act of discovery. To explore under the South Pole's glaciers is, in a way, to accept that some knowledge must come slowly. The ice has taken millions of years to form. It can wait a little longer to reveal itself. And while we wait, we study what we can. The ice above those hidden lakes preserves a timeline of Earth's climate. Each layer traps bubbles of ancient air, frozen moments from hundreds of thousands of years ago. By studying those cores, scientists can read the planet's breathing patterns, when it warmed, when it cooled, when volcanic ash darkened its skies. In that sense, the ice itself is already a record, a book of Earth's memory written in layers of snow. Beneath that record lies another story, one we can barely glimpse, where water moves in the dark untouched by the surface world. Standing at a drill site on the Antarctic plateau surrounded by endless white, a person could easily forget there's a whole hidden realm below. The silence is total. The air is so dry that sound barely travels. When machinery stops, there's nothing. No birds, no rustle, no echo. Just the feeling of the planet holding its breath. Somewhere under that stillness, water laps against rock. Maybe microbes drift in complete darkness, waiting out centuries between chemical pulses. Maybe entire ecosystems exist beyond what our definitions of life can handle. And maybe, for now, the best way to protect that possibility is to leave it alone. Yet leaving it alone doesn't mean ignoring it. It means understanding the boundaries of what we can safely reach. It means designing instruments that can observe without disturbing. It means learning patience on a geological scale. Every discovery in Antarctica reminds us of the balance between curiosity and restraint. We can measure, model and theorize, but there's a line we haven't yet crossed. And maybe that line, the thin frozen barrier separating us from what lies below, is what keeps the wonder alive. So as we settle deeper into this quiet journey, keep in mind that the story beneath the South Pole's glaciers isn't about conquering a frontier. It's about recognizing one that refuses to be conquered. It's about the limits of technology, the ethics of exploration, and the humility of knowing that some worlds are better observed than disturbed. The ice will remain, shifting slowly, hiding its rivers and mountains, preserving its secrets in cold silence. And as the night deepens and our thoughts drift with it, we'll keep descending, not physically, but through understanding, toward the heart of this frozen continent. Because to know why we can't truly explore under the South Pole's glaciers, we first have to understand what's really down there, how it moves, how it breathes, and why touching it might change everything. When people imagine Antarctica, they picture a blank white expanse at the bottom of the globe, a smooth sheet of ice stretching endlessly in every direction. It's a simple image, easy to draw on a map but completely misleading. Beneath that white emptiness lies one of the most complex landscapes on Earth, a place of hidden peaks, trenches, and lakes that twist and merge like veins under skin. And yet, even after decades of research, we still can't draw it properly. The South Pole's underside remains an unfinished sketch, a shape known only through faint echoes, gravity readings, and educated imagination. It's a map we can't quite make, and that might be one of the most haunting truths in modern science. The first attempts to understand what lay beneath Antarctica's ice came long before anyone thought of subglacial lakes or buried mountain ranges. In the early 20th century, explorers hauled sleds across the frozen plateau with compasses and notebooks, measuring distances by pacing and timing the movement of their dogs. They thought of the continent as a flat, featureless plain. A few ridges appeared on the horizon, but nothing suggested what waited below. When radar technology arrived decades later, it changed everything. Suddenly, scientists could bounce radio waves off the rock under the ice and measure the time it took for the echoes to return. The deeper the bounce, the longer the delay. These early surveys revealed that the continent wasn't flat at all. It was a maze of valleys, ridges and basins, some deeper than the Grand Canyon. The discovery was thrilling, but also deeply frustrating, because it opened a mystery we still haven't solved. Every radar map of Antarctica is incomplete. The ice doesn't cooperate with our instruments. In some regions, it's so thick and pure that radar signals scatter, bending and fading before they reach the rock below. In others, layers of frozen water and compressed snow distort the reflections, making them look like terrain that doesn't exist. Even satellites, which can sense tiny variations in gravity and magnetism, can only hint at what's under there. They tell us where the ice is thinner or thicker, where mass shifts or bulges, but not the exact shape of the world beneath. What we end up with are ghost maps, beautiful but uncertain outlines that scientists spend years debating. Each update erases and redraws parts of the continent, like an artist revising a sketch without ever seeing the real thing. There's something almost humbling about that. In an age where we can see the surfaces of Mars and the moons of Jupiter in exquisite detail, the fact that we still can't clearly picture what's beneath our own planet's ice feels like a quiet reminder of how little control we really have. It's not for lack of trying. Huge international collaborations like BedMap and IceBridge have spent decades flying radar-equipped aircraft over the polar plateau, tracing invisible valleys and hidden lakes. The data they collect fills supercomputers, generating 3D models that look like alien worlds. Yet even those models are riddled with blank spots. The gaps aren't small, they cover hundreds of square kilometres, especially in East Antarctica, where the ice is at its thickest and oldest. It's as if a painter had to guess entire parts of a landscape based on shadows alone. The reason mapping matters so much isn't just curiosity. The shape of the land beneath the ice determines how the ice itself moves, melts, and reshapes the world around it. Beneath the glaciers are troughs and ridges that guide rivers of frozen water, influencing how quickly the ice sheet flows toward the ocean. If we knew that map perfectly, we could predict how Antarctica might respond to climate change, where it will thin, where it will hold, how fast the oceans might rise. But without a clear picture, every model comes with uncertainty. We're trying to forecast the future of the planet on top of a landscape we can't see. In some ways, this challenge mirrors the way humans have always explored the unknown. Before satellites, sailors mapped the seas by following stars and guessing at coastlines. Their charts were filled with blank spaces labelled "Here be dragons," a kind of shorthand for what they didn't understand. Antarctica's underside is our modern dragon. Not mythical, but just as elusive. Every new radar scan fills a bit more of the blank, but the deeper we look, the more questions appear. Beneath the East Antarctic ice sheet, for example, lies a region known as the Aurora Subglacial Basin, a depression so vast that, if the ice melted, it could form a sea larger than the Mediterranean. But how deep it really is, what kind of rock lies under it, and how water moves through it are questions we can't yet answer. Then there are the buried mountains, the Gamburtsev Range, which stretch for over 1,000 kilometres beneath the ice. When scientists first detected them in the 1950s, they were stunned. The peaks appeared as sharp as if they'd been carved by glaciers only yesterday, even though they're buried under miles of ice. How such a mountain chain could form, and why it remains so well preserved, is still a puzzle. Some believe the ice itself acts as a kind of preservative, shielding the range from erosion. Others think geothermal heat from below continually reshapes it, keeping it sharp. Either way, the Gamburtsevs are proof that the Earth still holds secrets in places we thought we'd already conquered. Mapping those secrets requires instruments that operate under conditions few machines can tolerate. The radar systems used in polar exploration must survive temperatures that can drop below minus 50 degrees Celsius, and winds that tear at antennas like sandpaper. Aircraft engines freeze if left idle too long. Ground-penetrating sensors need to be calibrated for ice that can change density and texture every few meters. Even the simplest thing, like refueling or replacing a part, becomes a logistical ordeal. There are no supply stores, no repair hangars, no quick fixes. Everything has to be brought in, tested, and then operated with the precision of surgery. Each data-gathering flight represents weeks of preparation and millions of dollars. Sometimes the results are breathtaking. Sometimes they're noise, useless echoes that reveal nothing new. What's fascinating, though, is how much scientists can infer from even partial data. A small change in radar reflection might suggest a layer of sediment or a buried valley. A slight anomaly in gravity measurements might hint at a mountain's presence. Computers combine thousands of these clues into virtual landscapes, but no one knows how accurate they really are. It's like trying to reconstruct a statue from dust blown in the wind. You might get the general outline, but never the fine details. That uncertainty is what keeps Antarctica's map in constant revision. Every few years, a new dataset redraws rivers, redefines basins, or uncovers features no one imagined. It's an ongoing conversation between instruments, algorithms, and imagination. Even as technology improves, there's a philosophical question hovering in the background. What does it mean to know a place we can't touch? A radar echo is not a photograph. It's a trace, an interpretation of a sound that bounced through kilometers of ice and returned distorted by pressure and temperature. When we look at a 3D map of Antarctica's underworld, we're seeing not the thing itself, but a statistical version of it. A model, beautiful but abstract. The real landscape, the one hidden in total darkness, might look entirely different. There might be caverns where we see solid rock, smooth plains where we expect chaos. Until we reach it physically, all our maps are educated guesses wrapped in digital precision. That ambiguity can be both inspiring and unsettling. For scientists, it's a challenge. For storytellers and dreamers, it's a rare invitation. It means that right now, beneath the most thoroughly studied continent on Earth, there are still unknown places. Entire valleys have never been named, entire lakes never seen. Somewhere down there, a river may be flowing quietly, shaping stone, creating small habitats for life that hasn't seen sunlight for 20 million years. We can imagine it, we can model it, but we can't yet draw it with confidence, and maybe that's what makes it so compelling. One of the reasons mapping is so difficult has to do with how ice behaves. Unlike rock, ice isn't static. It flows, warps, and bends under its own weight. That movement distorts radar signals and shifts landmarks over time. A valley that appears in one survey might seem deeper or shallower in another, not because the instruments were wrong, but because the ice itself moved. In a sense, Antarctica refuses to be pinned down. It's a living, shifting map that redraws itself slowly but constantly. Trying to chart it is like trying to photograph a river by freezing one frame of motion. This constant change makes Antarctica both a scientific puzzle and a metaphor for how we approach the unknown. We tend to think of exploration as a quest for permanence, as if once we've mapped something, we've mastered it. But in the case of the South Pole's glaciers, the act of mapping is never done. The terrain underneath doesn't stay still long enough for us to declare victory. It's a humbling reminder that knowing isn't always a final state. Sometimes it's an ongoing relationship, a dialogue between our curiosity and the world's quiet refusal to yield. In the 1990s, when researchers first started piecing together a continental-scale map of Antarctica's underside, they faced an almost absurd challenge. The radar data came in fragments from different decades, collected by teams using different instruments and calibration methods. Stitching those fragments together required not just computing power, but creativity. They had to decide which versions of reality to trust more. If one dataset suggested a valley where another saw a ridge, they had to weigh which signal was clearer, which instrument more reliable. The result wasn't a definitive map, but a compromise between possibilities. Over time, as more surveys filled the gaps, the picture sharpened. But it never fully solidified. There are still areas, especially near the East Antarctic interior, where no radar has ever returned an echo from the bottom. Those blank spots are like pieces of a jigsaw puzzle that refuse to fit. It's tempting to think that we could just send more satellites, build stronger radar, or drill deeper. But each approach hits limits. Satellites can't see through ice thicker than a few kilometers with clarity. Airborne radar can't cover every square kilometer of a continent the size of the United States and Mexico combined. Ground-based surveys move slowly and require teams to endure months of isolation. Drilling, while possible, is expensive and risky. The deeper you go, the greater the chance of equipment failure, contamination, or collapse. For now, no single method can reveal the whole picture. We're left with mosaics stitched together from what little the ice allows us to glimpse. There's also the issue of time. Every expedition window in Antarctica is short, just a few summer months when temperatures rise enough for machines to function and planes can land safely. The rest of the year, the continent sleeps under darkness and storms. That means progress happens in bursts. Each season yields a little more data, a few more echoes, a slightly better understanding. Then the long winter erases the footprints, buries the markers, and resets the stage for next time. Exploration here is measured not in kilometers, but in patience. And yet, despite the obstacles, the allure never fades. Scientists return year after year because they know that every new scan, every new reading, adds another piece to a mystery no one else on Earth is solving. They talk about Antarctica's subglacial world the way astronomers talk about distant galaxies, with awe, with humility, with a sense that even a small discovery could change everything. There's a quiet poetry in that, even if no one calls it that out loud. It's the kind of fascination that drives people to endure cold, exhaustion, and isolation, all for the sake of seeing a landscape no human eyes will ever directly witness. In the end, the map we can't draw isn't just a scientific limitation. It's a symbol of how exploration has changed. We used to think discovery meant planting flags and taking photographs. Now it often means decoding signals and respecting boundaries. Beneath Antarctica's glaciers lies a world that resists intrusion but invites imagination. We can't stand on its shores or sail its dark waters, but we can listen, infer and learn. And maybe that's enough for now. As the data accumulates and the models improve, the unseen continent below becomes a little less mysterious, but only just. The deeper scientists peer, the more the landscape shifts like a mirage. It's as if the ice wants to remind us that some knowledge comes with conditions, that understanding requires patience, precision, and sometimes acceptance of the unknown. The map we can't draw remains unfinished, but perhaps that's its quiet purpose, to keep us curious, to keep us listening. And as we continue this journey into the depth of the frozen world, the picture beneath the South Pole becomes more than a mystery of geography. It becomes a story about time itself, about how ice preserves the memory of the planet while hiding its face. Ahead lies the question of how old this frozen world truly is, how long it's been building its silence, and what traces of the past still linger trapped within it. To understand why we can't fully explore what's beneath, we have to step backward into the deep history written inside the ice itself. When you stand on the Antarctic plateau and look around, you might think there's nothing there but snow and wind. But under your feet lies something extraordinary, not just in space, but in time. The ice beneath the South Pole is not simply frozen water, it's a layered record of Earth's history, built flake by flake over millions of years. Each layer is a year, each trapped bubble a moment, and together they form one of the longest and most detailed archives our planet has ever written. To walk across that frozen plain is to step across centuries stacked on top of one another, compressed into silence. It's hard to imagine the weight of so much time pressing down, but that's what Antarctica holds. Miles of frozen memory that stretch back to long before humans, before cities, before even the shape of the continents as we know them. The age of Antarctic ice depends on where you are. Near the coast, where glaciers flow quickly into the sea, the ice might be only a few thousand years old, constantly renewed by snowfall and melting at the edges. But in the heart of East Antarctica, near places like Dome Sea or the Vostok Station, the ice is ancient, hundreds of thousands, even millions of years old. The layers there are so thick that the bottommost ones were formed when the world was a completely different place. Forests grew in what is now desert, ocean currents moved differently, and the air held more carbon dioxide than it does today. That air, once free, is now trapped in microscopic bubbles sealed inside crystals of ice. To drill down and collect it is like breathing in the atmosphere of the distant past. When scientists extract ice cores, they're not just looking for frozen water, they're searching for clues, tiny chemical fingerprints that tell stories about temperature, volcanic eruptions, sea levels, and even cosmic events. Every layer carries traces of dust, pollen, and isotopes that change depending on the planet's climate. By studying these variations, researchers can reconstruct Earth's climate cycle, going back almost 1 million years. They can see ice ages come and go, trace abrupt warming events, and measure how the planet's heartbeat has changed over geological time. It's one of the most powerful tools we have for understanding our own fragility. But the deeper they drill, the harder it becomes. Not just physically, but conceptually. The oldest ice lies close to the bedrock, where heat from the Earth and the slow flow of glaciers distort the record. Those lower layers are compressed beyond recognition, warped like pages in a book that's been soaked and frozen for eons. We know they exist, but reading them clearly is another matter. To imagine what lies under all that ice, it helps to picture time itself as a kind of vertical landscape. At the surface, you're standing in the present, snow that fell last winter, maybe even last week. A few meters down, you're already into the era of ancient civilizations. A few hundred meters deeper, the ice age still reigns. Keep going, and soon you're in a world where mammoths still walk and human ancestors are learning to shape tools. Descend further, and you leave the human timeline entirely, entering epochs where the rhythm of the planet was driven purely by the tilt of its axis and the pull of the sun. Eventually, somewhere near the bottom, you might reach ice that formed before our species even appeared. It's a quiet, almost eerie realization. Beneath the South Pole, there's a tangible archive of a world that no one remembers, but which still exists in solid form, one molecule of water at a time. Scientists have a phrase for what they're looking for: oldest ice. It sounds simple, but the search for it has been one of the most challenging quests in modern glaciology. The idea is to find a place where ice has been preserved for at least 1.5 million years, long enough to capture the transition between two major climate cycles in Earth's history. That period, known as the mid-Pleistocene transition, marked a shift from shorter, more frequent ice ages to the longer, deeper cycles that shape our current climate rhythm. Understanding why that change happened could help us predict what's coming next. But finding ice that old, intact, and readable is like trying to find a single, unbroken thread in a tangled spool that's been crushed under mountains for eons. There are clues, of course. Radar mapping shows where the ice layers fold and where heat from the Earth might be melting the base. In some places, the ice is too disturbed, stirred by flow and refreezing. In others, it may have been thinned or lost altogether. Only a handful of regions, mostly in East Antarctica, seem to hold the right conditions: stable, cold, and undisturbed. There, the ice builds up faster than it melts, locking away history in an almost perfect deep freeze. Scientists working in those areas drill cores that can reach more than 3 kilometers deep. The work takes years, sometimes decades. A single core might be only 10 centimeters wide, but inside that narrow cylinder is the breath of ancient forests, the smoke of old volcanoes, the quiet record of snowstorms that fell before humanity began to write its own. The deeper those cores go, the stranger the data becomes. The composition of the air shifts, showing swings in carbon dioxide and methane that reflect ancient ecosystems. Dust layers mark global droughts or massive eruptions. Even the tiny crystals of the ice itself tell stories. How quickly they grew, how much stress they endured, how they slid over each other under pressure. Some layers are so old and compressed that the boundaries between years blur into each other. It's like reading the end of a book where all the words have merged into one long paragraph. But even blurred, the message is clear. The planet has always changed, sometimes slowly, sometimes violently, always in cycles that stretch far beyond our comprehension of time. It's ironic in a way that the very ice preventing us from reaching the world beneath it also gives us such a perfect record of the world above it. The same glaciers that hide subglacial lakes and mountains are also archives of everything that's ever fallen from the sky. Dust from deserts, smoke from distant fires, traces of meteoric particles, all of it captured and preserved in layers of snow that never melted. The Antarctic ice sheet is both a barrier and a library. We can't explore what's under it, but we can read what's within it, and what we find there shapes our understanding of everything else. Some of the most surprising discoveries from ice cores come not from the chemical analysis, but from what's alive inside them. In the oldest samples, scientists have found dormant microbes, still intact after hundreds of thousands of years. They're not alive in the usual sense, but they're not entirely dead either. Given the right conditions, moisture, nutrients, a bit of warmth, they can revive. It's as if the ice carries within it seeds of ancient life, waiting for a chance to wake. That resilience adds another layer of wonder and caution to Antarctic exploration. If microorganisms can survive for such immense spans of time in near total isolation, what might be living in the liquid water beneath the glaciers, where conditions are more stable? And if we find life there, what does that say about the possibilities beyond Earth? The timescales involved in Antarctic ice are hard for the human mind to grasp. 100,000 years is already beyond anything in our collective memory. 1,000,000 years is almost meaningless in everyday terms. Yet when you think about it in layers, it becomes easier to visualize. A single centimeter of ice might represent a few years of snowfall. A meter could hold decades. A kilometer contains tens of thousands of years. At the deepest points, the ice sheet is nearly 5 kilometers thick, meaning that somewhere near the base lies snow that fell when the continents were in slightly different positions, when global sea levels were higher, and when the climate patterns that govern today's weather hadn't yet formed. Working with that kind of timeline requires a particular kind of patience. Drilling through miles of ice is not fast work. The process is meticulous, lowering the drill, collecting a core segment, bringing it up, documenting every centimetre and repeating. It can take years to reach the deepest layers, and even then, interpreting what those layers mean takes longer. Teams of scientists around the world analyse each sample, comparing results, cross-checking data, trying to separate genuine signals from contamination. The patience required rivals that of archaeology, but instead of ruins, they're uncovering the memory of a planet. Sometimes, when the drilling stops and the machinery powers down, the silence in those remote research stations is overwhelming. Outside, there's nothing but wind and white. Inside, The cores sit in insulated containers, each one a column of time. It's hard not to imagine the vastness of what's still buried below, the miles of history we haven't yet reached. Every metre of untouched ice is another page of a book still sealed shut. And unlike most books, this one is irreplaceable. Once we disturb it, it's gone. That's why ice core projects proceed with almost reverent caution. The knowledge they seek is precious, but so is the medium that holds it. The story of Antarctica's ice is also the story of how the planet changes itself. The layers record every fluctuation in temperature, every pulse of greenhouse gases, every era when the balance between ice and ocean shifted. By studying them, scientists can see how delicate that balance really is. The patterns are clear. When carbon dioxide rises, temperatures follow. When it falls, the planet cools. Those cycles have been natural for millions of years, driven by orbital variations and volcanic activity. But in the last century, the changes have accelerated faster than anything in the ice's record. That realization gives the frozen timeline a sense of urgency. It's not just a curiosity, it's a warning. The ice shows us how the planet responds to imbalance, and it doesn't respond gently. It's easy to romanticize the idea of ancient ice, to imagine it as a still, perfect monument to the past. But it's not inert. It moves. Slowly, imperceptibly, the entire sheet creeps toward the sea, carrying its layers with it. The oldest ice isn't just old, it's distorted by motion, stretched and folded like dough under pressure. That movement is what makes drilling so tricky. A core taken from one location might contain ice from several eras jumbled together. Scientists have to decode those distortions using isotope analysis and flow models, reconstructing the true order of time from the chaos. It's an intricate dance between physics and patience, and even with the best tools, much of it remains guesswork. Sometimes, the ice reveals something unexpected. In a few cores, scientists have found layers of ash from ancient volcanic eruptions so powerful that they left traces across both hemispheres. Others contained fragments of meteoric dust, evidence of impacts that once changed global weather. These tiny inclusions are like footnotes in the planet's autobiography, small but crucial reminders that Earth's history isn't just gradual change but sudden dramatic upheaval. The fact that all of it is preserved in frozen form beneath the South Pole gives Antarctica a kind of quiet authority. It's not just a landscape, it's an archive of everything the world has endured. For all the precision of modern science, though, there's still something almost personal about the way researchers talk about the ice. They describe the feel of a freshly extracted core, the sound it makes when it cracks, the shimmer of air bubbles that once floated above prehistoric seas. They speak of it with the same respect others reserve for art or history. And perhaps that's fitting, because the ice is both a natural artwork carved by time and a historical document written in the language of molecules. To hold a piece of it is to hold a piece of the planet's own memory, still cold, still alive in its own way. The deeper scientists go, the more they realize that the story the ice tells is incomplete. Beneath the oldest layers, where the temperature rises from geothermal heat, the ice begins to melt. That thin zone, where solid turns to liquid, is where the record stops. Below it lies the unknown, the world of subglacial lakes, sediments, and hidden currents. It's there that the boundary between past and present blurs completely. The ice above speaks of what was, but the water below moves with what is. That's where geology, biology, and physics meet, and where the mystery of why we can't fully explore takes on its sharpest form. And so, as we follow this trail downward, through miles of frozen time, we begin to understand that Antarctica's glaciers are more than a physical barrier. They're a chronological one. They separate the world we know from one that has been sealed away since before our history began. To reach it, we must first listen to the ice itself, to the patterns in its layers, to the story it's already willing to tell. Only then can we even begin to approach what lies beneath. The living water, the hidden lakes that breathe in the dark, waiting in the cold for us to understand them without breaking them open. Somewhere far beneath the ice, where no sunlight has ever reached, where pressure squeezes water into slow motion and temperatures hover just below freezing, there are lakes. They aren't frozen solid as one might expect. They are liquid, sealed away under the weight of the Antarctic glaciers. They have been there for millions of years, untouched, unseen, and alive in ways we barely understand. Calling them lakes almost feels inadequate, because they aren't like any lakes on the surface. They're entire hidden ecosystems, black and silent, with chemistry that doesn't match anything we know from the open world. We call them subglacial lakes, and in a literal sense, they are the only parts of Antarctica that move with a quiet pulse. They are the lungs of a buried world, breathing slowly in darkness. It seems impossible that liquid water could exist in such a place. The temperature at the base of the ice is far below zero, the pressure immense, the air absent. Yet the very weight of the ice creates heat through friction and pressure. The Earth itself adds a bit more from below, radiating warmth from its core. The combination is enough to keep pockets of water from freezing completely. Those pockets form networks of hidden reservoirs, some as large as inland seas, others no more than thin veins of water threading through rock and sediment. Scientists believe there are over 400 of them scattered beneath the Antarctic ice sheet, connected by rivers that flow slowly, maybe centimetres per year, through channels carved into the bedrock. The largest of them, Lake Vostok, lies buried under nearly 4 kilometres of ice and holds more than 5,000 cubic kilometres of water. It's been sealed off from the atmosphere for at least 15 million years. The existence of these lakes was suspected for decades before it was confirmed. In the 1960s, Russian researchers working at the Vostok station noticed strange radar readings, echoes that didn't match the usual patterns of ice and rock. They saw flat, consistent reflections that hinted at something smooth and liquid. For years, the idea seemed too extraordinary to believe. How could there be liquid water under so much ice? It wasn't until the 1990s that satellite radar confirmed it. The signals showed a massive area of unusually flat reflections stretching across more than 200 kilometres. There could be only one explanation: a lake, as vast as some of the Great Lakes trapped beneath the glacier. It was one of the most startling geographical discoveries of the 20th century. Since then, more subglacial lakes have been detected using ice-penetrating radar and gravity measurements. Some are large and deep, others small and shallow. Many of them appear to fill and drain over time, meaning that there's an active hydrological system beneath the continent. Water moves under the ice the way blood moves through veins, slowly, rhythmically, keeping the glacier alive from below. It's not stagnant. It flows, melts, refreezes, and flows again. In that movement lies one of the keys to understanding Antarctica's behaviour. The lakes act as lubricants, allowing glaciers to slide toward the sea. Changes in their volume can alter how quickly the ice above moves, which in turn affects sea level and climate patterns far beyond the pole. In a way, the hidden lakes of Antarctica are not just features of a frozen world, they're gears in a planetary machine. But it's what might live in them that captures the imagination. These lakes have been sealed off from the surface for longer than humans have existed. No sunlight reaches them. They're under immense pressure, oxygen poor, and isolated from the rest of Earth's biosphere. If any organisms exist there, they've had to adapt to conditions unlike anywhere else. They might be microbial life forms that derive energy from minerals in the rock instead of sunlight, feeding on chemical reactions between water and the Earth's crust. Such organisms exist in other extreme environments, deep-sea hydrothermal vents, underground aquifers, and even within Antarctic ice itself. It's not a stretch to imagine that similar life could survive below the glaciers, sustained by chemistry rather than photosynthesis. This is why scientists are so cautious about exploration. A single probe contaminated with surface bacteria could alter an entire ecosystem that's been stable for millions of years. That's not just a scientific concern, it's an ethical one. It forces us to think about the value of knowledge versus the responsibility of preservation. We want to know what's down there, but do we have the right to disturb it? The debate isn't theoretical. In 2012, Russian scientists finally drilled through to Lake Vostok after years of preparation. Their drilling fluid, designed to prevent the borehole from refreezing, contained kerosene and freon, chemicals that could contaminate the water. When the drill finally broke through, the pressure of the lake forced water up into the borehole, where it quickly froze again. The sample they recovered was a mixture of refrozen lake water and drilling fluid, impossible to analyse cleanly. Critics argued that the project compromised one of the most pristine environments on Earth before we ever had a chance to study it properly. Other teams took a different approach. At Lake Whillans, beneath the Ross ice shelf, scientists used a sterile hot water drill to melt their way down 600 metres of ice without chemical lubricants. The operation required an entire mobile laboratory transported across the ice by tractor. Every piece of equipment was sterilised, every hose flushed with filtered water. When they reached the lake, they collected samples with extreme care, ensuring that nothing from the surface entered the environment below. What they found surprised everyone. The water contained living microbes, tiny, slow-moving organisms feeding on carbon and nitrogen compounds. It was proof that life could exist completely isolated from sunlight, thriving in conditions similar to those found on icy moons like Europa. It was a triumph not just of science but of restraint. The team had touched another world without breaking it. Even with that success, we've only just begun to understand what these lakes are like. Each one is different. Some are hypersaline, rich in dissolved minerals. Others are fresher, possibly fed by melting ice rather than groundwater. Some have sediments at the bottom that may contain fossil DNA, while others are too deep to sample without risk. They vary in pressure, temperature and chemistry, each representing a different experiment in nature's resilience. What unites them is their isolation. No sunlight, no atmosphere, no connection to the open ocean. It's a kind of planetary quarantine, maintained by ice. That isolation also makes them time capsules. The sediments at the bottom of these lakes might contain records of ancient climates, perhaps even traces of organisms that lived on the continent before it froze over 30 million years ago. In that sense, the lakes are not only biological but geological archives. They hold the story of Antarctica's transformation, from a warm forested land to the frozen desert we know today. Unlocking that story requires delicate balance. Too little exploration, and we remain ignorant. Too much, and we risk losing the very thing we seek to understand. To reach even one of these lakes safely demands technology that borders on science fiction. The drills must penetrate kilometres of ice while remaining sterile. The equipment must function in sub-zero temperatures without contaminating the environment. The power requirements are enormous, and communication with the surface is limited. Once a probe enters the water, it must withstand pressures higher than those in the deepest parts of the ocean, transmit data through miles of ice, and then return, if it can. In many cases, the probes are single-use. They descend once, gather what data they can, and are left behind as silent witnesses. The expense and complexity of such missions mean they happen rarely. Each one is a gamble, years in the making, for the chance to glimpse a world that exists entirely without light. Despite the risks, the fascination persists because of what these hidden lakes represent. They are analogues for extraterrestrial oceans. The icy moons of the outer solar system, Europa, Enceladus and Ganymede, are believed to have subsurface oceans beneath their frozen crusts. If we can learn how life endures in Antarctica's subglacial lakes, we might understand what conditions allow it to exist elsewhere. In a strange way, drilling through Antarctic ice is a form of planetary rehearsal. We are practicing how to explore other worlds by first learning how to approach our own without harm. But the lakes also challenge our perception of what exploration means. They remind us that discovery doesn't always require intrusion. Much of what we know about them comes from remote sensing, listening rather than touching. By measuring subtle changes in ice surface elevation over time, satellites can detect when a lake fills or drains. These fluctuations tell us that water is moving beneath the ice, connecting distant reservoirs like a hidden bloodstream. It's a slow, unseen network that links the continent together. The fact that we can detect such motion from space, without ever opening the ice, shows how much patience has become part of modern exploration. Sometimes the most responsible form of discovery is the one that leaves no footprint. It's hard to overstate how alien this environment is. Imagine standing above Lake Vostok, on a surface of featureless ice, with nothing visible to suggest that below you lies a body of water larger than some countries. The lake's surface is under more than 300 atmospheres of pressure, enough to crush metal. The water itself is near freezing but liquid because of that immense weight. It may contain gases like nitrogen and oxygen at concentrations far higher than seawater, trapped there for millions of years. Its sediments could hold a fossil record of ancient microbial life, or even chemical signatures that resemble early Earth conditions, and yet, for all we speculate, we've barely touched it. The real lake remains undisturbed, a sealed chamber of deep time. The concept of breathing in the dark might sound strange, but it fits. These lakes do breathe, in a sense. They fill and empty through subglacial channels, expanding and contracting as the pressure and flow change. Satellite data show the surface of the ice above rising and falling by several meters as lakes beneath them drain or refill. This cycle of movement is slow and quiet, but it reveals that even in complete darkness, the Antarctic continent is alive with motion. The lakes are not static pools. They're part of a dynamic system that redistributes water, heat, and nutrients under the ice. That slow rhythm is as close to a heartbeat as the frozen continent has. What makes this world so compelling isn't just its mystery, but its reminder of limits. We live in an era that values exploration, data, and access. We build machines to map the ocean floor, to scan distant planets, to quantify every corner of our environment. Yet under Antarctica's glaciers lies a place that resists that instinct. A world that forces us to pause. It demands a different kind of curiosity, one grounded in restraint, patience, and respect. The more we learn, the more we realize that our tools, though powerful, are blunt compared to the precision of nature's design. There's a certain humility in knowing that the most advanced technology on Earth still struggles to reach water that's been quietly existing just a few kilometers below us. The lakes also challenge how we think about life's boundaries. If microbes can survive in these conditions without sunlight in freezing temperatures under immense pressure, it expands our definition of habitability. It suggests that life doesn't need comfort, just opportunity. It can adapt, persist, and endure in ways that defy expectation. That realization doesn't just affect biology, it touches philosophy. It forces us to reconsider the uniqueness of our own environment. Maybe Earth's extremes aren't exceptions, but examples of how common resilience might be in the universe. The thought that something might be swimming, growing, or dividing under the South Pole's glaciers isn't science fiction anymore. It's a plausible truth waiting for evidence. And yet the same conditions that make those lakes fascinating also make them unreachable. The ice above them is too thick, the logistics too immense, the ethical concerns too heavy. We can model, we can measure, we can listen, but to truly explore them might require a leap of technology we haven't yet achieved. For now, we must be content with glimpses, with the knowledge that something extraordinary exists beyond our reach. It's a rare feeling in science, to know and not know at the same time, to sense the presence of an entire hidden biosphere, but remain unable to touch it. That tension, the pull between discovery and preservation, is what makes Antarctica such a powerful symbol of modern exploration. As the surface teams pack up their equipment, and the long polar night begins again, the lakes below continue their slow breathing undisturbed. The water flows, the microbes, if they exist, drift through currents unseen. The ice above thickens slightly, sealing them deeper into isolation. And somewhere in that darkness, history keeps accumulating in silence. Above, the wind reshapes the snow into new patterns, and on the surface, humans wait for another season, another chance to listen. What lies below remains what it has always been, self-contained, ancient, and alive in a way that doesn't depend on our observation. The more we learn about those hidden lakes, the clearer it becomes that what lies beneath Antarctica is not a void but a system, a vast interconnected underworld that sustains itself without sunlight. But that system exists under incredible weight, and it doesn't sit still. The glaciers that cover it move and shift constantly, pressing down with the massive continents, grinding rock, creating heat, and shaping the land beneath. The lakes aren't floating in isolation. They live under the weight of a continent, moulded by forces that never stop, and that weight, relentless and invisible, is what we must understand next, because it's the reason exploration here is so difficult, and the reason the world beneath remains beyond our full reach. The idea of ice as something fragile, something that melts in a glass or drips from rooftops, doesn't fit when you're standing on Antarctica. Here, ice is not delicate, it's not even passive. It's heavy, ancient, and endlessly patient. It's the weight of an entire continent pressing downward, reshaping everything it touches. Underneath that white stillness lies pressure so immense that rock bends and the crust itself adjusts in slow surrender. The glaciers of the South Pole are not just frozen water, they're an active geological force, a slow-moving mountain of mass that sculpts the planet. When we speak of what lies beneath them, we're really talking about what happens when that much weight presses down on time itself. The Antarctic ice sheet is the largest single mass of ice on Earth, holding about 60% of the planet's fresh water. In some places it's more than 4 kilometers thick, and in others, the ice sits directly on bedrock that lies below sea level. The total weight is so enormous, about 26 million gigatons, that it literally depresses the crust of the Earth beneath it. That depression is known as isostatic adjustment, and it means that Antarctica is, in a sense, sitting inside its own footprint. The land beneath the ice has been pushed down over millions of years, forming basins where water collects, where sediments pile up, and where mountains once tall enough to touch the sky now crouch under layers of frozen mass. To grasp what that kind of weight does, imagine pressing your hand into soft clay and leaving it there for 1,000 years. The clay would reshape itself, sinking deeper, compacting under the pressure. Now multiply that by billions and stretch it across a continent. The Earth's crust beneath Antarctica behaves a bit like that clay, slowly deforming under load. Where the ice thickens, the land sinks. Where it thins, the land rises again. This constant balancing act is one of the quiet movements of the planet, imperceptible on human timescales, but monumental across millennia. And it's still happening right now. As parts of Antarctica lose ice due to warming, the land beneath is beginning to rebound, rising centimetre by centimetre each decade. The Earth remembers the weight that pressed it down, and when that weight shifts, it moves in response, as if taking a long, slow breath after an age of stillness. But while the crust moves in these subtle ways, the ice itself behaves like something between a solid and a fluid. It flows, though so slowly that from the surface it looks motionless. The weight of the upper layers forces the ice below to deform and creep outward, spreading toward the coasts. The movement is measured in meters per year, yet over centuries it can reshape landscapes. Beneath that movement lies friction, ice grinding against rock, producing heat, carving valleys, and pulverizing stone into fine glacial dust. This grinding releases minerals into the subglacial water, feeding chemical reactions that may sustain microbial life. It also creates pockets of meltwater that lubricate the ice's movement, forming pathways for the hidden rivers that flow toward the sea. That frictional heat is one of the reasons the lakes beneath the glaciers remain liquid. Even though the air temperature above Antarctica can drop below -70 degrees Celsius, the heat generated at the base of the ice, combined with geothermal warmth from the Earth's mantle, is enough to keep some of the water from freezing completely. In effect, the ice sheet insulates itself. It traps the heat it generates, recycling it in slow motion. That self-sustaining balance, cold preserving its own heat, makes Antarctica an environment of contradictions, where immense cold and immense weight coexist in an equilibrium that has lasted for millions of years. When scientists talk about the weight of Antarctica, they're not just referring to physical mass, but to the consequences of that mass. Every year, as ice accumulates or melts, it changes the planet's gravity field ever so slightly. Satellites equipped with gravimeters can detect these shifts. When parts of the ice sheet thin, the gravitational pull there weakens, altering the way water circulates in nearby oceans. This means that Antarctica doesn't just respond to global change, it contributes to it. Its weight influences tides, sea levels, and even the distribution of ocean currents. The planet feels its presence the way a mattress feels the shape of a sleeper. When that shape changes, everything else adjusts. In some areas, particularly under the East Antarctic ice sheet, the pressure at the base is so intense that the ice is thought to fuse with the rock beneath, locking the two together. In other regions where meltwater pools and flows, the ice slides more easily, gliding on a thin film of liquid. These differences determine how fast glaciers move and where they might eventually collapse. One of the most studied examples is the Thwaites Glacier in West Antarctica, sometimes called the Doomsday Glacier because of how rapidly it's retreating. It's held in place by a combination of its own weight and the ridge of rock beneath it. As warmer ocean water seeps underneath, the ice loses its grip, destabilizing the glacier. If Thwaites were to collapse entirely, it could raise global sea levels by more than 0.5 meter, triggering further changes around the world. The event wouldn't happen all at once, but the process is already underway. The weight that once pinned the continent down is now becoming unbalanced, shifting toward the sea. To understand what happens under that kind of stress, researchers use radar and seismic instruments to listen to the ice move. The sounds are strange, low rumbles, distant cracks, long sighs that echo through the ground. These aren't sudden events but ongoing murmurs, the voice of pressure releasing itself slowly. Every crack and tremor tells scientists where the ice is slipping, where it's stuck, and how much strain it's holding. Over time, these measurements build a map of the continent's inner mechanics, a record of how its immense weight translates into motion. It's like listening to the heartbeat of a giant that moves so slowly it's easy to forget it's alive. That movement has another effect. It erases. Beneath the ice, rocks are ground to powder, mountains are smoothed, valleys are deepened. Whatever ancient landscapes once existed, they have been reshaped beyond recognition. When the first radar images of Antarctica's bedrock emerged, scientists were shocked to find how dynamic it was. Ridges, basins, even networks of what looked like old river channels now filled with ice. These features are the fossil remains of a world that existed before the continent froze, when Antarctica was covered in forests and teeming with life. The ice didn't just cover that world, it remade it. Its weight sculpted the land into something entirely new, sealing the past beneath the geology it created. This immense, unrelenting pressure also affects the very nature of the ice itself. At the surface, snowflakes fall light and crystalline. Over time, they're buried, compacted, and transformed into dense glacial ice. The deeper the layer, the more the individual crystals fuse together, expelling air and aligning under stress. Near the base, after thousands of years, the ice behaves less like a brittle solid and more like a viscous material flowing around obstacles. It's this transformation, from delicate snow to solid mass to near fluid motion, that gives the Antarctic ice sheet its strange dual nature. It's both rigid and alive, both still and constantly moving. Because the ice moves outward under its own weight, the edges of the continent act like a kind of slow-motion conveyor belt. Ice flows from the interior toward the coast, breaking off as icebergs into the Southern Ocean. This carving process is part of the natural cycle, but the balance between accumulation and loss is delicate. When melting at the base accelerates due to warming, the glaciers thin faster than new snow can replace them. The result is a kind of chain reaction. The weight distribution shifts, the land beneath rebounds, and the flow patterns change. Even a small alteration in temperature or ocean current can amplify this feedback loop. The system is stable only because of its scale, and that stability is under pressure in more ways than one. What's remarkable is how interconnected everything is. The weight of the ice determines how water flows beneath it. The movement of that water affects how heat is distributed. The heat influences melting, which changes the ice's weight again. It's a self-regulating but fragile loop, one that can tip into imbalance easily. Scientists often describe it as a dance between gravity, temperature, and time. It's not a metaphor, they mean it literally. Every gram of ice exerts force. Every shift in that force changes something else. And somewhere within that vast feedback system lies the reason we may never fully explore what's beneath. The very mass that preserves Antarctica's secrets also makes them unreachable. To explore under a glacier, you have to overcome its pressure. Drilling through kilometers of ice means working against forces strong enough to crush steel. Even if a borehole is opened successfully, it begins to close almost immediately as the ice flows to heal itself. The deeper you go, the faster that closing happens. It's like trying to hold open a wound that insists on sealing shut. The immense overburden pressure also means that any cavity created by drilling risks collapsing or flooding. Equipment must be designed to survive not just cold but crushing compression. And if it fails, there's no rescue. Whatever is lost becomes part of the ice. That sense of finality is part of why scientists approach these missions with such caution. Every probe lowered into the depths must be sterilized, pressurized, and often sacrificed. Once it's gone, it's gone. The ice will close around it, erasing the entry point as though it were never there. The glacier doesn't keep records of our attempts, it only keeps its own. This quality gives Antarctica an almost indifferent authority. It doesn't resist exploration out of hostility, it simply absorbs it. It outlasts us without trying. The power of that weight can also be seen in how the continent interacts with the planet's oceans. As glaciers slide into the sea, their mass redistributes water globally. The gravitational pull of the ice sheet draws ocean water toward it, creating a subtle but measurable bulge in sea level around Antarctica. When the ice melts and loses mass, that pull weakens, and the water redistributes elsewhere, raising sea levels in regions far from the poles. This is why melting at the South Pole can affect coastlines thousands of kilometers away. The planet's systems are not separate, they're continuous, bound by the pull of the same gravity that keeps the ice rooted in place. Even beneath all that mass, life finds ways to persist. Scientists have found microbial communities within the basal ice, feeding on minerals and surviving off the faint chemical energy generated by pressure and friction. These organisms don't see light, don't breathe oxygen, and don't need warmth. They exist because the weight above them provides stability, shielding them from radiation and preserving liquid water. The same pressure that makes exploration nearly impossible also creates a niche where life can exist without interruption for geological spans of time. It's another contradiction. What crushes also protects, what buries also preserves. When you consider all of this, the idea of truly exploring beneath the South Pole's glaciers begins to look almost paradoxical. To reach that world, We would have to overcome the very forces that define it. We would need to remove or penetrate the ice without altering the pressure, the temperature, or the purity of the environment. Even our most advanced technology struggles with those demands. Every attempt to reach the subglacial world risks disturbing its balance. The continent's weight doesn't just make it physically inaccessible, it makes it ethically complicated. To explore it is to change it, and to change it is to lose the very thing that makes it unique. The glaciers, in their immense silence, remind us of scale. They make human effort feel both small and extraordinary. We can map their surface, measure their thickness, even predict their movement, but we cannot undo their pressure or their patience. They move in time measured not by seconds or years, but by the rise and fall of continents. The weight of Antarctica is the weight of deep time made visible, a living monument to endurance. Beneath it the world continues. Water flows, sediments shift, microbial life persists, all under a crushing stillness that we can only observe from above. As the ice presses downward, it shapes more than the land. It shapes our understanding of limits. It forces us to recognize that exploration has boundaries, not because of lack of curiosity, but because of the fundamental physics of the world. Some doors remain closed not by choice, but by nature itself. And perhaps that's part of the balance. The ice keeps its secrets not out of defiance, but out of inevitability. It exists under pressure because it must. And yet, for all that weight, for all that power, the continent is not unbreakable. It listens, it shifts, it releases echoes that travel through the ice and reach us as faint vibrations, data on screens that tell us what's happening below. Those echoes are the next step in our journey, our way of seeing without touching, hearing without breaking. They are the whispers through which we continue to explore, moving from pressure into sound, from weight into resonance, from the dense silence of the glaciers into the delicate art of listening to the ice itself. There's a kind of silence in Antarctica that doesn't exist anywhere else on Earth. It's not the peaceful quiet of a calm night or the muffled hush after snowfall. It's heavier than that. It's the silence of absence, a silence so complete it seems to swallow sound. At the South Pole, even the air feels reluctant to carry noise. The cold thickens it, slows vibrations, absorbs them before they can travel far. You can shout and hear almost nothing come back. No echo, no resonance, just the sound of your own breath inside your hood. Machines too fall victim to this silence. It's not that they stop working immediately, it's that the environment strips them of endurance, eats away at them piece by piece until all that's left is stillness again. The phrase, "a silence that eats machines," isn't poetic exaggeration. It's what engineers and scientists actually face when they try to work in the Antarctic interior. The continent resists intrusion in the most practical ways possible. Electronics seize up in the cold, lubricants congeal, batteries drain within minutes. Even metals behave differently, contracting and warping as temperatures plunge. Every piece of equipment must be modified or reinvented just to survive. The problem isn't just the temperature, though it can drop below -80 degrees Celsius. It's the combination of cold, dryness, and isolation. There's no moisture in the air to carry heat, no vegetation to buffer wind, no sound to warn of mechanical strain. The result is a kind of invisible corrosion, one that happens not through rust or decay, but through silence and time. When researchers first began operating at the South Pole in the mid-20th century, they discovered that ordinary tools and instruments lasted a fraction of their expected lifespan. Cables would snap from brittleness, plastic casings shattered like glass, even fuel lines froze despite insulation. Radios would fail because the metal coils inside contracted differently from their housings, breaking delicate connections. The solution was to overbuild everything, to make machines heavier and simpler, to reduce moving parts to a minimum. But even then, the ice and cold had ways of finding weaknesses. Nothing lasts long without constant care, and care is a luxury when you're working in a place that tries to erase evidence of your presence the moment you look away. The atmosphere itself contributes to the slow breakdown. Antarctica's air is so dry that it pulls moisture from materials, desiccating rubber, plastic, and even the oils that protect metal. The ultraviolet light during the summer months adds another layer of punishment, degrading exposed surfaces in ways similar to radiation. A machine left outside for one season can emerge looking decades older. Inside the ice tunnels and boreholes, the challenges are different but equally unforgiving. Temperatures remain constant, but the pressure builds. Instruments must be able to operate under hundreds of atmospheres, their sensors sensitive enough to detect subtle changes in conductivity or temperature without shorting out. One failed seal or miscalibrated sensor can ruin an entire expedition's data. What makes this all the more difficult is how remote these operations are. When something breaks, there's no repair shop, no replacement parts waiting nearby. The logistics of bringing even small components can take months. Every tool and cable has to be shipped in by plane or overland traverse, often through storms that can last for weeks. Engineers plan meticulously, knowing that if a machine fails at depth, it's probably gone for good. Sometimes they never even know what went wrong, just that the signal stopped, that the silence returned. That silence isn't just metaphorical. When you work under the Antarctic sky, surrounded by endless white, there are moments when you realise that you can hear your own heartbeat more clearly than the hum of the generator beside you. The cold dampens everything, and the snow absorbs vibrations like a perfect acoustic sponge. When equipment finally powers down, either intentionally or from failure, the world seems to vanish into stillness. It's a silence that feels less like the absence of sound, and more like the presence of something vast and indifferent. The machines we build, the signals we send, all seem temporary against that scale. The same silence extends underground. When probes descend through the boreholes into subglacial water, they enter an environment where sound travels differently. Ice conducts vibrations faster than air, but it also bends and scatters them in unpredictable ways. Signals weaken. Communication becomes erratic. Engineers design instruments with redundant systems, knowing that some channels will inevitably fail. Sometimes the data stops mid-transmission, the last readings frozen in memory before the device succumbs to pressure or power loss. Those fragments, half-complete temperature profiles, partial chemical readings, become part of the archive, clues to something unreachable. Each loss is felt like a whisper fading into static. Some of the earliest subglacial missions were almost heroic in their persistence. In the 1990s, attempts to lower mechanical probes into boreholes near Lake Vostok ended abruptly when the devices froze in place. The heat from the probe created a thin film of water around it, which refroze instantly, trapping it forever. Later efforts tried to use hot water drills to melt paths downward, but even those systems faced limitations. The deeper they went, the more difficult it became to maintain temperature and pressure balance. The ice wanted to close to reclaim the space, to undo the intrusion. It's a reminder that glaciers are not static. They're always moving, even if slowly. Every hole drilled into them is a temporary wound, one the ice heals without effort. Modern technology has improved, but the core challenge remains. The Antarctic environment devours machinery not because of malice, but because it operates on timescales and energies far beyond human design. Electronics are built to last years. The ice thinks in centuries. A robot may function for a week or a month, but the glacier that swallows it continues flowing long after, indifferent to the attempt. For every successful data transmission, there are countless silent failures buried in the ice. Lost sensors, frozen cables, entire systems entombed forever. Somewhere beneath the South Pole, there's likely a layer of abandoned machines, each one a small testament to how fragile technology becomes in the face of the planet's endurance. To prepare for these conditions, teams design redundancy into everything. They build 3 versions of every sensor, 2 backups for every line of communication. They test equipment in environmental chambers that mimic Antarctic conditions, temperatures below -70, near vacuum dryness, continuous vibration. Yet even after such preparation, the real ice finds new ways to challenge them. Unexpected ice crystals form on lenses, clogging cameras. Pressure differentials crush protective casings. Thermal gradients short out wiring. Each failure becomes a lesson written in the language of silence. The psychological effect of that silence shouldn't be underestimated either. For scientists stationed at remote drilling sites, days and weeks pass without any natural sound except wind. The absence of noise becomes oppressive. It changes how time feels. The mind begins to magnify small sounds, the ticking of an instrument, the hum of a generator, the crunch of boots on snow. When those sounds stop, even briefly, the brain interprets it as something catastrophic. Every silence carries tension because it might mean another failure, another broken link between human effort and the world below. And yet, despite all this, we keep returning. There's something magnetic about the challenge itself, something deeply human about trying to push against the limits of endurance. Engineers talk about Antarctica with a mix of frustration and admiration, as if it were a living thing with personality. They describe how ice creeps into joints and cables, how it shifts overnight, how it reclaims equipment with slow precision. They call it the great equalizer, the environment that humbles machines. Even the strongest designs are temporary here. The silence doesn't just eat machines, it digests their arrogance. The effect isn't confined to the surface. In subglacial exploration, even the simplest technical problems can cascade into mission-ending failures. A single kink in a cable can sever power or data transmission. A miscalibrated pressure valve can cause implosion. One of the most infamous examples happened during a British attempt to reach Lake Ellsworth. After years of preparation, the team began melting through 3 kilometers of ice with a specially designed hot water drill. The operation required maintaining 2 continuous boreholes, one for the drill and one for circulation water, to prevent refreezing. The plan depended on precise alignment, but somewhere along the way, the holes diverged. The water system lost pressure, and the entire operation had to be abandoned. Millions of dollars, decades of planning, all undone by physics and silence. The equipment was left behind, sealed in by the glacier, becoming part of the landscape it had tried to explore. These failures aren't wasted, though. Each one teaches something about the nature of the ice, about how materials behave in extreme conditions. The silence isn't just a void, it's feedback, in its own way. Every stopped signal, every missing response tells scientists where the limits are. It's a conversation of sorts, one-sided but ongoing. The ice doesn't speak, but it answers through what it allows and what it denies. In that sense, the silence that eats machines isn't destruction. It's a boundary marker, the line between what we can reach and what remains its own. Even communication between surface teams can be challenging. Radio waves behave strangely at these latitudes, bending and scattering due to atmospheric conditions. During storms, static drowns out all transmission. In deep field stations, isolation becomes total. If a machine fails or a generator shuts down, help is not just far away. It's unreachable until the weather clears. The people who work there learn to trust redundancy more than optimism. They know that the environment doesn't negotiate. They build systems that can survive without attention, knowing that sometimes the only reliable backup is the silence itself. There's a strange irony in how this silence also protects the purity of the continent. The same conditions that destroy machines also preserve what lies beneath. The lack of noise, vibration and disturbance means that the ecosystems and sediments under the ice remain untouched. The continent maintains its own balance by being inhospitable to intrusion. It's not just a place, it's a filter, one that lets only the most careful exploration pass through. That's part of why so much of Antarctica remains pristine. Human technology struggles to leave a lasting mark, and yet, when machines do work, the data they return can be transformative. The few successful probes that have reached subglacial environments have recorded chemistry, temperature, and microbial activity that reshape our understanding of life on Earth. Those small victories come at immense cost and risk. Each one represents years of failure distilled into a moment of success. Every bite of data pulled from the ice is a kind of defiance against silence, proof that persistence can extract whispers from a world designed to mute them. Still, the ice doesn't change its nature. It continues to flow, to press, to reclaim. The silence always wins in the end. The question isn't whether we can conquer it, but whether we should keep trying to. There's a lesson in how quickly the environment dismantles our presence. It reminds us that not all mysteries are meant to yield easily. Sometimes, resistance itself is part of what defines the mystery. The machines fail, but in doing so they teach us humility, the recognition that there are forces and scales of time beyond our control. The term Antarctic silence has even become a shorthand among engineers for describing impossible environments elsewhere. Space agencies study it when designing equipment for icy moons or Mars, because the conditions, cold, dryness, pressure, isolation, are similar. What fails in Antarctica would fail on Europa. The continent is our testing ground for survival beyond Earth. Every sensor that dies there contributes to future exploration elsewhere. In that sense, the silence that eats machines at the South Pole might one day help us listen more carefully in places even colder, even more distant. But for now, here on Earth, the lesson remains immediate. The ice isn't an enemy, it's a reminder of scale. It forces us to build better, think slower, and accept limits. When the generators fall silent and the wind settles, what's left isn't defeat but perspective. The continent existed long before our machines, and it will exist long after. The silence that eats machines is the same silence that preserves the past, that keeps ancient water flowing in darkness, that protects the fragile balance beneath. Above ground, the surface stations flicker with artificial light against the vast white. Below, the cold continues its quiet work. The ice shifts slightly, swallowing another fragment of steel, another cable, another piece of human ambition. The machines are temporary, but the silence remains, patient and absolute. It is both barrier and guardian, both destroyer and preserver. And within that quiet endurance lies the next part of this journey, what survives in spite of it. Because even under the crushing weight and consuming stillness, there are things that persist, things that adapt, things that live. What comes next isn't about what we build, but what endures without us, in the hidden places where the silence itself becomes the environment. Beneath the frozen world, where sunlight has never existed and pressure rules every inch, the water that moves under Antarctica's glaciers carries more than cold and weight. It carries secrets. This liquid darkness, trapped between ice and rock, is not just a geological curiosity. It's a living record of everything the Earth has hidden away for millions of years. The water flows unseen, slow and ancient, forming lakes, channels, and thin films that shift quietly as the glaciers above them move. It's easy to think of that world as dead, sterile, too cold for anything to persist. But inside those shadows, something continues. Chemical reactions, microbial life, slow transformations of rock and water that happen at a pace beyond our perception. What lies beneath the ice doesn't simply exist, it endures. The first time scientists drew water from beneath the ice, they were prepared for disappointment. It seemed impossible that anything could survive there. No light means no photosynthesis, no energy from the sun, no source for complex ecosystems. The pressure and isolation would destroy most known forms of life, yet the samples told a different story. Under the microscopes back at their temporary laboratories, researchers saw movement. Not much, no darting fish or waving plants, but tiny, deliberate motion. Microbes. Alive, slow, almost unrecognizable. but unmistakably alive. In that moment, the entire definition of habitability shifted. Life didn't need sunlight. It didn't need warmth. It needed chemistry, patience, and the ability to adapt. These organisms, found in places like Lake Whillans and the sediments beneath the Taylor Glacier, survive by feeding on minerals and gases released from the bedrock. Iron, sulfur, nitrogen. Simple elements turned into the currency of survival. Some bacteria oxidize iron the way surface organisms burn sugar. Others reduce sulfate, converting it into energy through chemical processes that resemble the metabolism of early Earth. It's not a thriving paradise of biodiversity. It's a minimalistic, stripped-down world, efficient to the extreme. But it works. These microbes form self-contained communities, recycling every bit of resource they have, living in a chemical loop that has gone uninterrupted for millennia. What makes this remarkable isn't just that life exists there, but that it does so in total isolation. The water under Antarctica has been sealed from the surface for hundreds of thousands, sometimes millions of years. Whatever life exists within it has evolved separately, adapting to an environment of constant darkness and high pressure. These ecosystems might represent the closest living relatives to early microbial life on Earth, the kind that thrived before the planet had oxygen, before it had sunlight in the way we understand it. To study them is to peer backward into our own biological history. Every sample, every microbe, every trace of DNA recovered from those subglacial environments tells us something about the resilience of life itself. The search for these secrets is delicate work. Scientists can't simply drill down, scoop water, and bring it to the surface. The risk of contamination is too great. One bacterial cell from human skin could outcompete an entire native ecosystem. That's why the methods used are as careful as surgery. The drilling equipment must be sterilized with ultraviolet light and hydrogen peroxide. The water used for melting must be filtered, heated, and refiltered before it touches the borehole. Even then, the teams work in full sterile suits, mindful that a single mistake could undo decades of effort. The samples are sealed immediately, preserved at the temperature of their origin, and handled with gloves that never touch the air. Once the samples reach laboratories, the analysis begins with restraint. Scientists look for signatures first, chemical evidence of metabolism, traces of isotopic shifts that suggest biological activity. Only then do they attempt to culture the microbes, often failing because the organisms refuse to grow outside their native pressure and chemistry. The success stories are rare but profound. Each living cell recovered from beneath the ice represents an independent solution to survival. Different lakes and channels host different microbial communities, shaped by the unique chemistry of their environments. Some rely on methane, others on ammonia, others on the slow dissolution of rock. Collectively, they form a mosaic of life that thrives without the conditions we once thought essential. The idea that such ecosystems exist has changed how scientists think about life elsewhere in the universe. When the Galileo spacecraft detected evidence of a subsurface ocean on Jupiter's moon Europa, researchers immediately thought of Antarctica. If microbes can survive under kilometers of ice here, shielded from the sun, then perhaps something similar exists there. The same applies to Saturn's moon Enceladus, which ejects plumes of water vapour from its frozen crust. The parallels are too strong to ignore. Antarctica has become a stand-in for alien oceans, a natural laboratory where the boundaries of biology are tested in real time. But the secrets beneath the glaciers aren't only biological. The water itself carries chemical stories written in its solutes and sediments. When meltwater flows over bedrock, it dissolves minerals, picking up elements that reveal the nature of the terrain below. By studying these traces, scientists can infer what kind of rock lies beneath, how it weathers under pressure, and how geothermal heat affects it. These clues are crucial because direct observation is nearly impossible. The chemistry of subglacial water serves as a proxy for geology, giving us a glimpse into the hidden structure of the continent. Some of those chemical signals hint at deep sources of heat, geothermal vents that might rise from fractures in the crust, releasing minerals into the lakes above. This heat doesn't melt the ice completely, but it maintains a stable liquid environment. It's another reason life might persist. The combination of geothermal warmth and chemical nutrients creates a rare pocket of stability in an otherwise frozen world. Every sample of subglacial water is a small piece of evidence that the earth beneath the ice is still active, still breathing heat into the cold. There's also the matter of the sediments at the bottom of these lakes. They're more than mud, they're archives. Each layer of sediment holds particles carried by water long before the ice arrived. Buried within them are fossilized traces of pollen, diatoms, and ancient DNA. These are remnants of Antarctica's warmer past, when the continent was part of Gondwana, covered in vegetation and flowing rivers. To drill into those sediments is to read the continent's biography, one that stretches from lush forests to frozen silence. The problem is that reaching them without contamination is almost as difficult as reaching the lakes themselves. Every sample is a compromise between curiosity and caution. Even without touching those sediments directly, researchers have learned a great deal from indirect evidence. Radar imaging shows how subglacial water pools and flows, carving invisible paths through the rock. Some channels are hundreds of kilometers long, connecting distant lakes and systems that rise and fall over decades. These movements can be detected from space as subtle shifts in the surface elevation of the ice. When one lake drains, the ice above it sags slightly. When another fills, it rises. The pattern is like breathing, slow, regular, and vital. It's another reminder that beneath the stillness of Antarctica, the planet is always in motion. One of the most intriguing discoveries came from studies of Lake Whillans, where microbial activity was measured even in sediments that had been isolated for more than 100,000 years. The DNA found there included genes for nitrogen and sulfur metabolism, clear evidence that the microbes were not just surviving but cycling nutrients actively. That means the ecosystem below isn't static, it's dynamic, self-sustaining. It might even evolve in response to slow changes in temperature, pressure, or chemistry. In that sense, Antarctica's subglacial world is a parallel biosphere, operating independently from the one above. It doesn't rely on the sun, on seasons, or on oxygen from the atmosphere. It runs on its own rules. The implications of this are immense. If life can persist there, in total isolation, then it raises questions about the resilience of life elsewhere on Earth. How many other hidden ecosystems exist in extreme environments, deep underground, within rocks, beneath oceans, thriving unnoticed? The more we look, the more we find that life isn't rare at all. It's adaptable. It seems to fill every available niche, no matter how inhospitable. The Antarctic subglacial world is perhaps the purest example of that adaptability. It's a demonstration of how life refuses to end, even when the environment appears terminal. Of course, there's a tension in this discovery. The more we learn, the more we risk altering what we study. Each probe, each drill, each human attempt to touch that hidden water introduces variables. Even with the best sterilization, the act of drilling changes pressure and temperature, potentially disturbing ecosystems that have existed in balance for eons. It's a moral dilemma unique to modern science. How to study without damaging, how to know without interfering. Some researchers argue that we should observe remotely and leave direct sampling for the future, when technology can ensure complete protection. Others believe that the knowledge gained is worth the risk, provided the work is done with care. Both views have merit, but the ice doesn't favour either. It waits, patient, indifferent to debate. The phrase liquid shadows captures something essential about these lakes. They are both lightless and revealing. Every time we uncover a bit of data about them, we see not just what they contain, but how much remains unseen. Their darkness isn't just physical, it's informational. It represents everything we haven't yet measured, everything we still don't understand about the interactions between ice, water, rock, and life. In that sense, the darkness isn't absence, it's potential. Each discovery illuminates a small part of it, and each unanswered question makes it larger again. Some of the most fascinating hypotheses about subglacial environments concern their role in global systems. The water that flows beneath Antarctica eventually drains into the ocean, carrying with it minerals and organic compounds. These outflows could influence marine ecosystems, providing nutrients that sustain plankton and other life forms near the coast. In that way, the hidden lakes and rivers of the South Pole might be linked to the health of the world's oceans. The connection between the deepest darkness and the most productive marine regions is not yet fully understood, but it suggests that Antarctica's secret world may be more than an isolated curiosity. It may be part of the planet's broader network of life. The study of these waters also challenges how we think about exploration. It's easy to romanticize discovery as something dramatic, full of noise and triumph. But here, discovery happens quietly. There's no rush of adrenaline, no roar of engines, just patient observation, careful calibration, and the faint satisfaction of seeing data that almost wasn't there. The scientists who dedicate their lives to this work understand that progress here is measured in microns and molecules. They may spend years preparing for a single sample, only to extract a few drops of water that hold an entire hidden history. The rewards are subtle but profound. Even the failures add depth to the story. A lost probe, a contaminated core, a frozen cable all become part of the record of how we've tried to reach this world. They are reminders of how delicate the balance is between human ambition and the natural systems that guard their secrets. The glaciers erase our tools, but not our intent. They remind us that exploration isn't always about success. Sometimes it's about persistence in the face of silence. Sometimes it's about learning how to listen differently. In the end, what we call secrets are really just truths we haven't earned yet. The ice holds them because it must, because its environment allows memory to exist without decay. The water moves quietly, keeping the past and present mixed together in perfect equilibrium. There's no malice in its secrecy, only the calm certainty of something that doesn't need to reveal itself. It's the same feeling that pervades every discovery in Antarctica, the sense that the planet doesn't owe us explanation, but that we owe it attention. And so, the story continues downward, from the microbes in their liquid shadows to the rivers that connect them. The journey under the ice is not a descent into stillness, but a deepening into motion. The hidden water flows, reshaping the rock beneath, carrying sediments, eroding, rebuilding. These invisible rivers link the lakes into vast subterranean systems, shifting slowly but constantly. They move like breath, pushing through cracks and channels, driven by the weight above and the heat below. To follow them is to trace the heartbeat of the frozen world, to understand how a continent can flow beneath its own silence. The rivers that move in darkness are the next part of this journey, where the frozen continent becomes fluid again, and the unseen world continues to write its story beneath our feet. Beneath the Antarctic ice, where pressure replaces gravity and sound is almost meaningless, there are rivers. They don't rush or sparkle. They don't roar or carve dramatic canyons like the rivers we know. They move in silence, in darkness, in intervals so slow they make time itself seem exaggerated. Scientists call them subglacial melt channels, but the term doesn't capture their reality. They are ghost rivers, streams of water that exist without ever being seen, tracing invisible routes across a landscape that no one has touched. They connect the hidden lakes, they carry sediments, they shift over decades and centuries, shaping the continent from below. They are the lifeblood of the ice sheet, though almost no one ever hears them flow. It took modern instruments to prove they were real. Before that, scientists assumed the base of Antarctica's ice sheet was mostly static, frozen solid. But as radar improved and satellites began to detect subtle movements in the ice, a new pattern emerged. Surface elevations rose and fell by meters, sometimes over just a few years, far too fast to be caused by accumulation or melting at the top. Something was moving below. When researchers compared these changes to radar maps, they found that lakes beneath the ice were filling and draining in cycles. That could only mean one thing: there were channels connecting them, and water was flowing between them under the pressure of the glacier itself. The discovery changed how scientists viewed Antarctica. It wasn't a frozen block, but a dynamic system, pulsing with motion. The ghost rivers beneath the glaciers were not relics. They were active, circulating water through the subglacial network, carrying heat and sediment, redistributing pressure. These rivers are unlike any others on Earth. They flow uphill as often as downhill, driven not by gravity alone but by pressure gradients in the overlying ice. In places where the glacier is thick, the pressure at the base can be so high that it forces water toward thinner areas against the slope of the bedrock. That means the rivers move according to invisible maps, shaped by forces we can't see directly. The scale of these systems is staggering. One study revealed that a single subglacial drainage basin beneath East Antarctica covered an area larger than the entire United Kingdom. Within it, dozens of lakes and channels connect in a complex web, filling and draining over timescales that range from months to millennia. The water that flows through them eventually emerges at the coast, either seeping into the ocean beneath the ice shelves or erupting through fissures that carve massive chunks of ice into the sea. In that way, the ghost rivers serve as the hidden engine of Antarctica's interaction with the global ocean. They regulate how heat and nutrients move between land and sea, how ice shelves gain or lose stability, and how the entire continent breathes through its frozen skin. But these rivers don't just move water, they move time. The sediments they carry are the remnants of ancient landscapes buried long before the ice arrived. Grains of crushed rock, fragments of fossilized life, traces of minerals, all are transported slowly through the subglacial system. When scientists sample meltwater emerging from beneath glaciers, they find chemical signatures that reveal the type of rock being eroded below. Those minerals tell stories of continents that existed when Antarctica was part of the supercontinent Gondwana. In some samples, traces of organic carbon suggest the remains of long-dead ecosystems, recycled endlessly through pressure and flow. The ghost rivers are geochemical archives, carrying whispers of a world that vanished 30 million years ago. The movement of these rivers is subtle but powerful. They can reshape the base of the glacier by melting and refreezing ice along their paths. When meltwater flows through a tunnel at the base, it absorbs heat from friction and pressure. As that heat dissipates, the water can refreeze further downstream, depositing ice in layers that build new ridges and hills. Over time, this process sculpts the landscape beneath the ice, creating undulating plains and channels known as mega-scale glacial lineations. From above, radar detects them as ripples tens of kilometers long. They are the footprints of rivers that no one has seen, carved not in rock but in ice and sediment, shifting slowly under pressures that defy comprehension. Even the bedrock beneath these rivers is not still. Under the immense weight of the ice, it flexes, sinks, and sometimes rises. The movement happens over centuries, but its effects accumulate. As glaciers advance and retreat, they scrape the ground clean, expose new layers of rock, and redistribute sediments across the continent. When the ice retreats, the land begins to rebound, a process that continues long after the glaciers have moved on. In this way, Antarctica's ghost rivers don't just shape the present, they record cycles of destruction and renewal that stretch back millions of years. Each flow, each freeze, each slow shift adds another layer to the continent's long conversation with gravity and time. Because we can't see them directly, scientists use radar, gravity, and seismic waves to trace these rivers. Each technique provides a different kind of evidence. Radar bounces signals through the ice. revealing smooth surfaces where water collects. Gravity mapping detects slight changes in mass, indicating liquid movement. Seismic surveys listen for echoes that behave differently in wet and dry conditions. Combined, these tools create an indirect portrait of motion in darkness. But the image is always incomplete, always shifting. The rivers themselves are not constant. They migrate, branch, and disappear as pressure and temperature change. A river mapped one decade may no longer exist in the same form the next. The landscape below is alive in slow motion. That motion matters more than most people realise. The stability of the Antarctic ice sheet depends on what happens at its base. If the subglacial water flows efficiently, it can lubricate the ice, speeding its slide toward the sea. If it drains away or freezes, the ice sticks, slowing movement. These small differences, multiplied across a continent, determine how quickly Antarctica contributes to global sea level rise. Understanding the ghost rivers is not a matter of curiosity, it's a matter of predicting the planet's future. The balance between frozen and flowing, between sticking and sliding, holds the key to how much the oceans will rise in the coming centuries. The difficulty is that we can't easily predict how those rivers behave under changing climate conditions. The heat that drives melting at the base comes from multiple sources: pressure, friction, and geothermal flux from the Earth's crust. As surface temperatures rise, more meltwater may reach the base through crevasses, altering the pressure balance. But the system's response is non-linear. In some regions, added water might increase lubrication, accelerating ice flow. In others, it might refreeze, locking the glacier more tightly to the bed. The ghost rivers respond not just to heat, but to geometry, chemistry, and time. Modelling them requires supercomputers, and even then the results carry uncertainty. There's also the mystery of how these rivers sustain themselves. They're not constantly replenished by surface melt, especially in the cold interior where snow never melts. Instead, they depend on internal heat and pressure. The ice at the base melts slightly under pressure, and that meltwater flows toward lower pressure zones, creating channels that maintain equilibrium. The process is self-organizing, driven by feedback between melting and flow. Where water moves, it erodes ice, enlarging its path. Where it slows, it refreezes, sealing itself off. The result is a network that maintains itself without external input, a system of persistence born entirely from physics. It's a natural mechanism that keeps the glacier alive from within, much like a circulatory system keeps a body alive in sleep. Some of these rivers connect to the ocean beneath the ice shelves, carrying meltwater that influences how seawater circulates under the floating ice. When warm ocean currents reach those points, they melt the ice from below, creating cavities and accelerating collapse. The interaction between subglacial rivers and the sea is one of the most important but least understood aspects of Antarctic dynamics. It's where the stability of the continent meets the energy of the ocean, a boundary so delicate that a small shift in salinity or temperature could change everything. Despite the complexity, the picture that emerges is one of balance. The ghost rivers aren't chaotic, they're structured by the rules of pressure and temperature. They form predictable patterns of drainage, responding to the topography of the bedrock and the thickness of the ice above. Over thousands of years, they carve routes that remain roughly stable, even as glaciers advance and retreat. In that stability lies continuity. The rivers beneath today's ice may trace paths once followed by rivers that flowed freely on the surface, back when Antarctica was temperate. The difference is that now they move unseen, carrying not water from rain but melt from ice, recycling the same molecules endlessly through darkness. If you could travel with one of these rivers, following its path from lake to ocean, the journey would defy expectation. It would begin in stillness at the base of an ice sheet where the temperature hovers just below freezing. The water would be viscous, dense, carrying microscopic sediments that grind against the bedrock. You would pass through narrow channels only centimetres wide, then widen suddenly into broad, slow-moving tunnels tall enough to swallow buildings. The walls of ice would glow faintly from the pressure of their own existence, translucent but never transparent. The current would be sluggish, measured in millimeters per second, yet unstoppable. You would pass regions of absolute darkness, then areas where minerals spark faint reflections under artificial light. You would see the floor shift, rock and sediment sliding underfoot as the glacier creeps above, reshaping everything in its path. There would be no sound except the distant groaning of ice, the slow grinding of Earth's patience, and eventually you would reach the ocean not in a burst of light, but in a seamless blending of fresh and salt, ice and water, time and motion. This journey, though imagined, mirrors what happens continuously beneath Antarctica. The rivers flow, the floors shift, and the boundaries blur. It's not a static world, but a living one, responding constantly to forces we barely measure. When scientists describe it, they speak with caution. They know how much of what they say is inference. Every model they build, every equation they test, depends on assumptions about conditions that can't be verified directly. Yet the coherence of the evidence suggests something profound. The ghost rivers beneath the ice are as fundamental to Antarctica's existence as its glaciers themselves. Without them, the ice would lock in place, losing its motion. With them, the continent breathes. The notion of a shifting floor adds another layer to this mystery. Under the glaciers, the ground itself is unstable. Some areas rest on sediment that behaves like soft clay, deforming easily under pressure. Others are anchored to bedrock that resists movement. As water flows through, it changes the balance of friction and weight, causing the ice above to slip or grip in different ways. These micro-movements can trigger large-scale consequences, such as sudden surges or collapses in glacier flow. In effect, the base of Antarctica is a moving puzzle, where every piece affects the next. The ghost rivers are the lubricant, the negotiators in the constant conversation between ice and rock. As researchers learn more, they begin to see Antarctica less as a frozen relic and more as a living machine, a complex system of interactions where even the slowest movements matter. The ghost rivers are part of its metabolism. They transfer heat, redistribute minerals and maintain balance. They're invisible but essential. Without them, the ice sheet would behave differently, perhaps catastrophically. With them, it endures, adjusting to stress with the patience of deep time. Still, the more we understand, the more fragile the picture becomes. The warming of the oceans and atmosphere threatens to disrupt this balance. As ice thins and the flow of subglacial water changes, the ghost rivers may accelerate, shifting patterns that have been stable for millions of years. That could destabilize the glaciers they support, leading to faster melting and sea level rise. The chain reaction would ripple outward, from the deep Antarctic interior to the coastlines of distant continents. It's a reminder that even the slowest systems are not immune to change, that even ghost rivers can shape the visible world, and yet, amid all that movement, there is still something unreachable about them. We can trace their paths, measure their effects, and model their behaviour, but we can't watch them directly. We know them through absence, through echoes, through the way the ice above rises and falls. They are proof that some truths can be known only indirectly, inferred through patience and persistence. The ghost rivers exist not because we see them, but because everything around them moves in response to their hidden flow. In that sense, they are the perfect symbol for the world beneath the glaciers, a world defined not by what we can observe, but by what we can sense only through its consequences. The ghost rivers remind us that exploration isn't always about visibility. It's about connection, about the ability to read patterns in darkness and understand that even in silence, everything moves. Beneath Antarctica, water continues its ancient journey. The floors shift, and the weight above presses down in endless rhythm. The continent endures, alive with motion too slow to hear, but powerful enough to shape the planet. And as we listen to those faint signals, the story doesn't end, it deepens. Because the same forces that create those rivers also create resistance. The ice and water interact in ways that test the limits of endurance, not only for machines, but for the idea of exploration itself. The environment pushes back, reminding us that every attempt to reach it carries consequences. What happens next isn't just about what flows, it's about what resists, what pushes upward when the weight becomes too much. What happens when the frozen world defends itself against intrusion? There's a limit to how far we can push against Antarctica before it pushes back. The ice, for all its stillness, has a kind of memory. It remembers intrusion. It remembers heat. It remembers movement. Every probe, every borehole, every human attempt to go deeper stirs that memory. It's not a conscious resistance, of course, but it feels like one. The environment doesn't rage or retaliate in the way living things do. It simply obeys the physics that made it. But those same laws are unyielding. When we try to force our way in, the ice responds with pressure, with collapse, with silence. It closes holes, seizes machines, refreezes paths we've barely opened. It's not malice, it's equilibrium. The ice fights back because it has to. One of the first lessons scientists learn when working in the Antarctic interior is that everything here seeks its own balance. The temperature difference between the surface and the base, the pressure gradient across the ice sheet, the constant gravitational pull downward, all of it is held in a fragile harmony. Drilling into that system, even with the best technology, disturbs it. The warmth from machinery melts the surrounding ice, creating a thin layer of water that can refreeze almost instantly. Cables freeze in place, boreholes collapse under their own walls, instruments are crushed, sensors fail, data stops. What's most humbling is that this happens without drama. There's no explosion, no sudden break, just the quiet inevitability of ice reclaiming itself. The process is mechanical, not emotional, yet it's difficult not to feel a kind of personality in the way the ice resists. It behaves like something that knows its own boundaries. The moment a hole is drilled, it begins to close. The moment heat enters, it spreads, then dissipates, and the cold wins again. It's a battle already decided before it begins. The only variable is how long the interruption lasts before the glacier resets to its preferred state, undisturbed, sealed, and silent. Temperature is the most obvious enemy, but it's not the only one. Pressure is more ruthless. At the base of the ice sheet, where kilometers of frozen weight press down, the pressure exceeds 400 atmospheres. Every instrument must survive those conditions without deforming, leaking, or collapsing. Even a slight miscalculation in structural design can mean failure. The ice doesn't tolerate weakness. When an instrument fails, it fails completely, crushed into unrecognizable fragments. The glacier absorbs what's left and continues to flow as though nothing happened. The destruction is absolute but quiet. The same principle applies to human activity on the surface. Stations built on the plateau are constantly shifting, sinking, or being buried by snow. The ice doesn't just sit still, it moves outward toward the coast. Every building, every antenna, every vehicle is caught in that flow. At the South Pole Station, for instance, the entire structure must be jacked up periodically to stay above the rising snowdrifts. Old campsites disappear, swallowed by accumulation. What was a level floor one year becomes tilted the next. In time, everything man-made becomes temporary. Even the most carefully engineered structures are reminders that permanence here is an illusion. The ice claims everything eventually. The deeper scientists try to go, the more unpredictable the ice becomes. Layers within the glacier behave differently depending on temperature, crystal size, and impurity content. Some sections deform easily, others resist. These differences create stresses that accumulate invisibly until something gives way. Cracks form, shifting deep within the glacier, altering pressure distribution. When that happens, an entire drilling path can warp or close unexpectedly. Instruments that work perfectly one day stop the next. It's not failure in the conventional sense, it's adaptation. The glacier changes shape to maintain its internal balance, and our efforts to penetrate it simply get caught in that slow rearrangement. The ice also carries its own internal weather. Static charges build up as crystals rub against each other under immense pressure. Sudden releases can interfere with electronic signals or fry delicate sensors. Even magnetic instruments suffer. Compass readings become unreliable. Communication lines generate noise that seems to come from nowhere. The glacier hums, clicks, and crackles in frequencies too low for human hearing. It's a living field of physics, constantly shifting, constantly active. Every attempt to measure it reveals how much more there is to measure. Then there's the issue of contamination, not from what we bring, but from what we disturb. The lower layers of the ice contain gases, particles, and microbes sealed away for millions of years. When we drill, those materials can be released, mixing ancient and modern environments in unpredictable ways. A borehole isn't just a tunnel. It's a time portal connecting two eras that were never meant to meet. The water that rises from below may carry chemical compositions from the past, reacting with air and instruments in ways we can't fully predict. In some projects, unexpected bursts of gas or changes in pressure have forced researchers to abandon operations. The ice doesn't explode like a volcano, but it resists violation by altering its own chemistry. The lesson, repeated across decades of exploration, is simple. The glacier always wins. Every machine we lower, every sensor we place, is temporary. Some instruments last a few months. Others fail within hours. A few endure for years, quietly transmitting data until the batteries fade or the cables shear under strain. When they stop, the silence returns. The glacier reclaims its equilibrium. And yet, despite knowing this, we keep trying. There's something irresistible about pushing against a boundary that refuses to yield. It's not stubbornness, it's curiosity shaped by persistence. At its core, the struggle between human technology and Antarctic ice is a dialogue between two vastly different timescales. Machines operate on human time. Seconds, minutes, years. The glacier moves in centuries. When the two interact, the mismatch creates conflict. We want results now. The ice responds later. Our instruments record data for a brief moment, but the processes they measure continue long after we're gone. It's like trying to photograph a moving mountain with a camera that only works for an instant. The result is never complete, but even fragments are valuable because they offer glimpses into a world that resists visibility. This resistance is not uniform. In some regions, the ice cooperates. Smooth, predictable, easy to model. In others, it becomes chaotic. Basal ice, the layer closest to the bedrock, is especially unpredictable. It contains impurities, sediments, and pockets of meltwater that alter its flow. In places, it sticks tightly to the rock, anchoring the glacier. In others, it slides freely. This variability means that two boreholes drilled just kilometers apart can yield completely different results. The ice is not one material but many, a mosaic of densities and behaviors. Its complexity defies simplification. What we call fighting back is simply the ice asserting its natural state. The same pressure that protects the subglacial lakes also destroys our equipment. The same flow that carries nutrients to hidden microbes drags our instruments out of alignment. Every obstacle we encounter is the result of the same physics that make the place extraordinary in the first place. The challenge isn't to overcome the ice, but to understand it on its own terms. That realization has shaped modern polar research. Instead of trying to conquer the environment, scientists now design missions that work with it, using passive sensors, remote observations, and autonomous systems that require minimal disturbance. The goal has shifted from intrusion to coexistence. Even so, accidents happen. Drills freeze, tethers snap. In one case, an autonomous probe designed to explore beneath an ice shelf went missing after its navigation system failed. Months later, When another team located the area using sonar, they found the probe had been carried away by shifting ice, trapped in a crevasse, its power long dead. The glacier had taken it, absorbed it, added it to its growing collection of artifacts buried in silence. Each loss adds another reminder of how delicate our presence here is. Sometimes the ice's response is immediate. When a borehole reaches a subglacial lake, the difference in pressure between the water and the hole can cause a sudden surge. The water rushes upward, refreezing almost instantly when it meets colder layers. The result is a plug of ice that seals the borehole shut, erasing the opening before it can be used. This phenomenon has ended more than one ambitious project. The message is clear: balance restored. No second chances. Other times, the ice's resistance plays out slowly, almost invisibly. The heat from drilling diffuses through surrounding layers, altering their structure. Over months, the changes accumulate. Crystals realign, stresses shift, and eventually the borehole collapses. The glacier heals itself not with speed, but with persistence. What was once an entrance becomes indistinguishable from the surrounding ice. It's an act of geological patience, restoration by indifference. The term self-healing ice might sound like a metaphor, but it's real. Ice flows under its own weight, redistributing material to close gaps and smooth surfaces. Even the tracks left by vehicles on the plateau fade quickly, erased by drifting snow and slow compression. Nothing lasts here except the ice itself. In that sense, the continent operates like a living archive with a perfect filing system. It absorbs disruptions, reorganizes them, and continues unchanged. The memory of intrusion exists only in the minds of those who made it. Yet despite its resilience, the ice is not invincible. It fights back, yes, but its strength depends on temperature and pressure. As global warming accelerates, that equilibrium is shifting. The same glaciers that once resisted every intrusion are now retreating faster than anyone predicted. The weight that once sealed the subglacial world is easing in places, allowing meltwater to escape more freely. The fight has turned inward. The ice is no longer pushing against us. It's struggling to maintain itself against the heat of a changing planet. The resistance that once protected its secrets may eventually fail, not because of human persistence in drilling, but because of the atmosphere we've altered. That irony isn't lost on the scientists who study it. They know that the race to understand what lies beneath is also a race against time. As the glaciers thin and the ghost rivers accelerate, the delicate balance of the subglacial world may change forever. Lakes that have been sealed for millions of years could drain. Sediments preserved in perfect stillness could mix with meltwater and flow into the ocean. The ice that once fought back might one day surrender, not in defeat but in transformation. The system that resisted exploration might open itself simply because it can't help it anymore. For now, though, the fight continues. Every expedition is a negotiation between persistence and respect. Scientists design lighter, cleaner, more adaptable tools. They use radar and satellite data instead of drills when they can. They learn to interpret signals instead of demanding direct access. The ice remains the final authority, setting the terms of engagement. It doesn't yield easily, and when it does, it demands care. The phrase, "when the ice fights back," captures more than the physical challenge. It also describes the psychological one. Working in such an environment changes people. The sense of isolation, the constant awareness of danger, the understanding that everything around you is stronger and older than anything you can build, it reshapes how you think about exploration. Many who return from Antarctica describe feeling humbled, even changed. They speak not of conquest, but of collaboration, as if the continent had taught them something about patience, scale, and restraint. The ice doesn't speak, but it communicates through limits, and those limits leave an impression deeper than any success. In the end, the resistance of Antarctica isn't just a technical obstacle, it's a reminder of boundaries. It tells us that discovery is not always about reaching farther, but about listening better. The ice pushes back because we push too hard, too fast, with tools built for worlds that don't forgive mistakes. When the ice reclaims our machines, it's not punishment. It's preservation. It keeps its own order intact, waiting for a future where exploration might mean understanding rather than intrusion. And so, as we step back from the pressure and the fractures, we begin to listen again. The ice that crushes our instruments still sends signals. It hums with seismic tremors. It whispers in radar echoes. It speaks in gravity and vibration. The fight gives way to conversation, a quieter, more enduring exchange. The resistance becomes delta. The collapse becomes insight. We stop forcing, start listening, and through that listening the continent reveals its next secret, not through access but through echo. The ice's defiance turns into information, and in that soundless communication lies the continuation of the story. After a while, silence itself begins to sound like something. Not music, not noise, but presence. The kind of sound that only exists when everything else has stopped. In Antarctica, that presence becomes a companion. You start to notice it between each gust of wind, in the way the air presses against your ears, in the faint hum that seems to come from nowhere and everywhere at once. For scientists who spend months on the ice, that silence becomes an instrument. They learn to listen, not just for survival, but for knowledge. Because buried beneath that stillness, the ice is full of echoes. Every fracture, every vibration, every distant shift sends waves rippling through the frozen world. And if you know how to listen, the continent begins to speak. Seismic listening is one of the few ways to explore what can't be seen. The idea is simple. Send a pulse into the ice and record how it returns. The speed, the strength, the shape of the echo tell you what lies beneath. But the execution is anything but simple. The signals have to travel through kilometers of solid ice, each layer with its own density, its own impurities, its own way of bending and scattering sound. By the time the waves return, they've been transformed, delayed, stretched. Turning them into information requires careful interpretation, a kind of conversation between the living and the inert. The first seismic experiments in Antarctica began decades ago, long before we had satellites to map the continent. Scientists used explosives buried in snow to send vibrations downward. The echoes that came back revealed a world no one had imagined. Mountain ranges buried under ice, deep basins filled with sediments, massive valleys where water once flowed. It was like hearing the voice of a hidden continent. Those early measurements were crude, noisy, but they showed that Antarctica was not a uniform sheet. It had structure, depth, and history. Each echo was a glimpse of a forgotten geography, a reminder that what looks static from above is anything but beneath. Modern instruments have made those echoes clearer. Instead of explosives, scientists now use vibroseis trucks, machines that shake the ground in controlled patterns, or arrays of sensors that detect natural vibrations from the Earth itself. These passive recordings capture the constant tremor of the planet, the micro-earthquakes, the creaks of shifting ice, even the low-frequency hum of ocean waves hitting distant shores. Antarctica is never completely still. It's just that its movements happen in a register below our hearing. Seismic sensors translate those inaudible motions into patterns we can read. The result is a portrait of the ice that's as dynamic as it is beautiful. Beneath the surface, the echoes reveal folds and fractures, ridges and plains, all sculpted by pressure and flow. Some areas ring like hollow chambers, suggesting hidden lakes or voids. Others return dull, thick echoes where ice and rock are fused tightly together. Each signal tells a story of movement and resistance, of flow and fracture. Scientists map these echoes over vast distances, building three-dimensional models that let them visualize the shape of the continent under the ice. But even with the best data, interpretation remains partly an act of imagination. The ice never gives up its full detail. It only allows approximations. Among the most fascinating discoveries from seismic mapping is the existence of buried mountain ranges. The Gamburtsev Mountains, for instance, hidden beneath more than 2 kilometers of ice in East Antarctica. When scientists first detected them, they were stunned. The range stretched for about 1,200 kilometers, as tall and rugged as the Alps. Yet it had been completely invisible. No one had ever seen a single peak. The echoes that revealed it were faint and fragmented, requiring years of analysis to piece together. It was like reconstructing an entire world from whispers. Those mountains may have been the nucleus around which the Antarctic ice sheet first formed. In that sense, they are the continent's spine, preserved in perfect secrecy for 30 million years. Listening to Antarctica isn't limited to seismic waves. Radar echoes play a role too, bouncing high-frequency signals off internal layers of the ice. These reflections reveal patterns that correspond to snowfall history, deformation, and flow. Some of the layers are remarkably continuous, stretching across thousands of kilometers, preserved like pages in a transparent book. Others are distorted or erased, showing where the ice has flowed faster or melted internally. Each layer is a record of climate and movement, a frozen chronicle of the planet's atmosphere written year after year. The echoes from radar instruments turn the ice into an archive, one that records both its own behaviour and the world above it. But not all echoes come from instruments. Some come from the ice itself. As glaciers move, they crack and grind against the rock below, releasing acoustic energy. These natural sounds, called ice quakes, are recorded by seismic networks as sharp pulses. They reveal when and where the ice is slipping, how fast it's moving, and how stress builds up within it. Thousands of such events happen every day across Antarctica, forming a symphony of motion that no one can hear unaided. To the senses, it's a language of creaks and snaps, each one a signal of adjustment, a release of pressure, a negotiation between ice, rock, and gravity. In one sense, these echoes are evidence of a living system. The ice is not passive, it's constantly adapting to stress, redistributing weight, responding to temperature. Each vibration, each tremor, is a heartbeat of the glacier. In another sense, they're reminders of impermanence. Every crack is a step toward change, toward melting, flowing, and eventually disappearance. Listening to these sounds is like listening to the breath of something immense and aging, something both powerful and vulnerable. The technology used to capture these signals is sensitive enough to detect movements smaller than a millimeter. Networks of geophones and radar stations listen continuously, feeding data to researchers thousands of kilometers away. They can track the motion of ice streams as they slide toward the ocean, watch the filling and draining of subglacial lakes in real time, and detect the smallest shifts in ice shells before they break apart. In recent years, scientists have begun to combine seismic and radar data with satellite imagery, creating an almost complete picture of the continent's inner motion. The result is both stunning and sobering. The ice is alive, yes, but it's also changing faster than ever recorded. The echoes are getting louder, the tremors more frequent, as warming accelerates the processes that once moved in silence. Beyond their scientific value, these echoes have a kind of philosophical weight. They force us to confront the scale of the forces at work, to hear the continuity of a planet that moves whether we pay attention or not. The Antarctic ice doesn't need us to notice it. Its movements existed long before human ears, long before machines. But now, for the first time, we can listen. And in that listening, we discover something unsettling. That the Earth itself communicates in ways we're only beginning to understand. It doesn't speak in words or intentions, but in patterns of vibration that carry information about stress, temperature, and flow. It tells us where it hurts, where it changes, where it releases energy. The challenge is learning how to interpret that language before it's too late to act on what it's saying. Some of the most profound seismic data comes from the edges of the continent, where ice shelves meet the ocean. These are places of constant interaction, where tides flex the ice up and down, where waves strike from below, where currents erode the base. The echoes recorded there are chaotic, overlapping, unpredictable. Yet within that noise, scientists have found patterns that correspond to daily and seasonal cycles. The ice shelves resonate like vast instruments, vibrating with the rhythm of the sea. The frequency of those vibrations changes as the shelves thin or crack, offering early warnings of collapse. In that sense, listening becomes a form of prediction. The echoes tell us what's about to happen before it does. There's something strangely human about the idea that we understand Antarctica better by listening than by looking. For centuries, exploration was about sight, about seeing what lay beyond the horizon. But here, where light reveals only whiteness, hearing becomes more meaningful. The data we collect doesn't produce images but waveforms, patterns of amplitude and delay. It's not about vision, it's about translation. The scientists who work with these signals often describe their work as interpretation rather than observation. They read the Earth like a score, each vibration a note in an endless composition. The ice also carries echoes from beyond itself. Meteorites striking the surface send vibrations through the crust. Distant earthquakes on other continents travel through the planet, refracting as they pass under the South Pole. Even ocean waves breaking thousands of kilometers away create infrasonic pulses that reach the ice. Antarctica is a receiver as much as a sender. It absorbs the world's noise, filters it, and sends it back altered. When researchers analyze the data, they can identify distant events by their seismic fingerprints. The continent, though isolated, is connected to everything. Its silence is not emptiness. It's filled with the faintest murmur of global motion. That interconnectedness has practical importance too. Seismic networks in Antarctica contribute to global monitoring systems that detect nuclear tests, track earthquakes, and study Earth's interior. Every echo recorded there adds a data point to our understanding of how the planet behaves. Beneath the frozen surface lies not only scientific curiosity but infrastructure, the kind that helps us measure the pulse of the entire Earth. In that sense, the ice is both participant and witness. It experiences the planet's movements and preserves their memory in vibrations that travel for thousands of kilometers. What's fascinating is how these echoes change with time. Over decades of listening, scientists have noticed subtle shifts in the background noise of Antarctica. Some regions hum differently now, their frequencies altered by thinning ice or changing pressure. The tone of the continent is evolving, reflecting the stress of a warming climate. This isn't metaphorical, it's measurable. The spectral characteristics of the seismic background have changed, showing that the ice is less stable, more fractured, more restless. The planet is speaking through resonance, and the message is clear even if the translation is incomplete. To stand on the ice and imagine these sounds is to realize how much of the world operates below the threshold of human senses. The continent hums constantly, a low vibration that only instruments can detect. If we could hear it directly, it might sound like the deep drone of a storm filtered through centuries of snow. It would be both terrifying and beautiful. The sound of pressure, friction, and flow merging into something continuous. Every glacier, every ice shelf, every subglacial river contributes to that chorus. Together they create the soundscape of an entire frozen world, a kind of planetary heartbeat amplified by cold. When you think about it, the fact that we can hear these echoes at all is remarkable. It means that even in the most silent place on Earth, communication persists. The ice, in its resistance, in its stillness, continues to send messages upward. We listen, record, interpret, and try to make sense of them. Each signal teaches us something new about structure, motion, and fragility. And even when the data is incomplete, even when the echoes fade before they return, there's value in the attempt. Listening, in itself, is an act of respect. The work of decoding these signals goes on year after year, often by people who never see the places they study. The data streams from remote stations, transmitted by satellite, analysed by teams across the world. They watch the numbers shift, the patterns change, the noise grow louder or fainter. The results are compiled into models, shared, debated, refined. It's a slow process, but one that feels necessary, because beneath all the science lies a simple truth. The planet is talking, not in human terms, but in its own deep, ancient language of movement and resonance. The ice doesn't care if we understand it, but we might need to if we want to stay in rhythm with the world that sustains us. And as the sensors continue to record, as the ice keeps shifting, the echoes don't stop. They move through the white abyss, bouncing between layers, scattering across basins, carrying the signatures of change. Each one adds to the archive of the invisible, the library of sound within silence. And somewhere in that vast collection of vibrations lies the next story. Not about collapse or resistance, but about what remains after the noise fades. Because even as the echoes travel and die, something stays behind, something constant, something waiting to be heard in a different way. Every story about Antarctica eventually reaches a moment when curiosity meets its limit. It's not a limit of imagination or ambition, it's one of responsibility. For every question we ask about what lies beneath the ice, there's a second question that follows quietly behind it. Should we? The deeper we go, the more fragile the balance becomes between discovery and disturbance. The continent holds not just scientific opportunity, but ethical weight. It's a place that demands restraint. A reminder that curiosity, unchecked, can become carelessness. Antarctica doesn't resist us because it fears intrusion. It resists because it depends on balance. Our challenge is to decide whether our search for knowledge honours that balance or undermines it. The tension has existed since the first human footprints appeared on the ice. Early explorers saw Antarctica as a frontier, something to conquer, to map, to claim. But as science replaced conquest, the language changed. We stopped calling it the last continent to be claimed and began calling it the last to be understood. Yet even understanding carries consequences. To observe something, you must interact with it. To measure it, you must change it, even if only slightly. The question is, how much change is acceptable in the pursuit of truth? In a place as delicate as the Antarctic ecosystem, even small actions echo for centuries. Modern Antarctic science operates under one of the most stringent environmental protection frameworks in existence. The Antarctic Treaty and its associated protocols forbid military activity, resource extraction, and most forms of pollution. Every research project, no matter how small, must justify itself not only scientifically but ethically. Before a team can drill, collect samples, or install sensors, it must demonstrate that the benefit of the data outweighs the risk of contamination. It's a unique situation in human history. An entire continent governed not by ownership but by agreement, protected for the sake of knowledge itself. And yet, even within that framework, the decisions are rarely simple. Take, for instance, the challenge of exploring subglacial lakes. These bodies of water have been sealed beneath ice for millions of years. No sunlight, no air, no contact with the surface. They are natural time capsules, preserving ecosystems and chemical compositions from eras long vanished. To access them requires drilling through several kilometers of ice, an act that inevitably alters the pressure and temperature of the environment. No matter how careful the technique, the mere act of opening a passage changes the lake's isolation. Scientists must decide whether the knowledge gained about ancient life, about Earth's history, about planetary biology, is worth the irreversible change that access creates. When the first attempts to reach Lake Vostok were planned, the debate was intense. The Russian team operating the site had already drilled to within a few meters of the lake's ceiling. Environmental groups warned that continued drilling could introduce surface microbes or chemicals that would contaminate a pristine ecosystem. The scientists argued that the data could redefine our understanding of life on Earth. Both sides were right. The lake was eventually breached, and the results were extraordinary. Microbial DNA unlike anything seen before. Traces of life that suggested entire ecosystems thriving in the dark. But whether those organisms were truly native or introduced during drilling remains uncertain. The line between discovery and contamination blurred, and the question of how to proceed became even harder to answer. Other teams, learning from that controversy, developed cleaner, more controlled approaches. Hot water drilling systems that sterilize the meltwater, pressure balancing methods that minimize environmental disturbance, and protocols for immediate sealing of boreholes after use. Yet even with these precautions, absolute sterility is impossible. The Antarctic ice is too reactive, too sensitive to disturbance. Every thermal pulse, every vibration, every chemical trace leaves a mark. It is not a question of if, but of how much. That realization forces scientists to view exploration not as extraction, but as conversation. Each act of curiosity must be matched with an equal measure of caution. The ethical dilemma extends beyond biology. The ice itself, as a climate archive, holds data we desperately need. Each core extracted from the ice sheet tells a story of past atmospheres, tiny bubbles of ancient air preserved in crystal. By studying them, we learn how carbon dioxide levels change through time, how temperature fluctuated, how volcanic eruptions shaped weather centuries ago. That information helps us predict the planet's future. Yet even here, the act of drilling carries impact. The core holes fill with fluid to prevent collapse, and that fluid must be carefully managed to avoid contamination. The drilling sites leave marks that persist for decades. Compared to industrial activity elsewhere, it's minimal. But on a continent defined by purity, even a footprint feels heavy. Curiosity drives all of it. It's the instinct that built science in the first place, the desire to understand how things work, to explain what lies beyond sight. Without it, there would be no discovery, no progress, no comprehension of the forces that shape our world. But curiosity alone is not enough. It needs boundaries, not to suppress it, but to refine it. Caution transforms curiosity from impulse into insight. Without caution, exploration becomes extraction. Without curiosity, caution becomes paralysis. The fragile line between them is where responsible science lives. For the people who work there, this balance is personal. Scientists in Antarctica are not thrill-seekers or adventurers. They are custodians of the unknown. They wake up knowing that their actions may leave marks invisible now but significant later. They handle ice cores with gloved hands, sterilize every tool, monitor every emission. The rules aren't bureaucratic, they're moral. When they lower a sensor into a borehole or sample air trapped for 1 million years, they're aware that they are the first and possibly the last humans to touch that piece of time. That awareness carries both awe and responsibility. Even communication about discoveries must tread carefully. The public wants excitement, revelation, bold headlines about new life beneath the ice. But scientists know how fragile those claims can be. Contamination, misinterpretation, incomplete data. Any of these can undo years of careful work. So they speak with restraint, even when the results are extraordinary. The language of Antarctic research is often understated, deliberately cautious. Behind every press release lies a quieter truth. Discovery here is fragile, conditional, temporary. The more we know, the more we recognize how much we might never be able to touch without changing forever. This careful approach extends to planning as well. Before any mission begins, environmental assessments are conducted to predict potential impacts. How will drilling affect local ice flow? Could fuel or heat alter subglacial chemistry? What are the chances of introducing contaminants? Teams simulate these scenarios in controlled environments before committing to real operations. It's not about perfection, it's about accountability. Each decision acknowledges the possibility of harm and attempts to minimize it. That awareness, built into the culture of Antarctic science, is what keeps the balance intact. And yet, there are moments when the balance wavers. Funding pressures, competition and national pride can nudge decisions toward risk. The allure of being first to reach a lake, first to find new life, first to map a hidden valley, can overshadow caution. The ice doesn't care about firsts, but humans do. The challenge is keeping that ambition aligned with responsibility. The Antarctic Treaty has helped, enforcing cooperation over competition. Data is shared, research is open, and discoveries belong to everyone. Still, the temptation remains. The more inaccessible a secret seems, the greater the desire to uncover it. The question, again and again, is how to satisfy that desire without crossing the line from respect to disruption. There's also a deeper philosophical side to this tension. When we say we want to know what's beneath the ice, what do we actually mean? Is knowing the same as touching, as sampling, as seeing directly? Or can knowledge come from inference, from listening to echoes, from interpreting patterns, from understanding without intrusion? The shift from physical exploration to remote sensing marks more than technological progress. It represents a change in mindset. It suggests that maybe the most ethical form of curiosity is the one that doesn't insist on contact, the one that listens instead of reaching. That idea resonates beyond science. The fragile line between curiosity and caution exists in every human endeavour, between invention and destruction, between progress and preservation. Antarctica just makes it visible. The continent functions like a mirror, reflecting back our behaviour at its most extreme. It shows us what happens when we approach something fragile with tools designed for conquest. It forces us to slow down, to measure not just what we do, but why we do it. It reminds us that knowing everything is not the same as understanding everything. Sometimes leaving something untouched is an act of deeper respect. Still, curiosity doesn't vanish because caution exists. It adapts. Scientists develop non-invasive techniques, drone imaging, satellite interferometry, ice-penetrating radar. These methods allow us to see through the ice without breaking it. They transform exploration from direct contact to remote connection. The data may be less immediate, but it's cleaner, safer, more sustainable. In a way, it's the next evolution of exploration, discovery without disruption. The more we refine these methods, the closer we get to understanding without altering. It's a kind of harmony between human ingenuity and natural endurance. The balance is also personal for those who spend years analysing samples in distant laboratories. They know that every vial of meltwater, every particle of sediment, represents a moment of intrusion. Their responsibility is to extract as much knowledge as possible from as little impact as necessary. They stretch each sample across dozens of tests, chemical, biological, isotopic, using minimal material. It's science practiced like conservation, where precision replaces abundance. The fewer holes we drill, the better we understand the meaning of each one. The fragility of this balance is perhaps the most important lesson Antarctica teaches. The ice sheet is immense, but it's not infinite. Its ecosystems are resilient, but they're not invulnerable. Human presence, even minimal, adds heat, waste, and disturbance. The environmental protocols that govern the continent aren't overcautious. They're essential. Without them, curiosity could quickly become exploitation. History is full of examples where the pursuit of knowledge turned destructive. Antarctica offers a chance to do better, to prove that exploration can exist alongside preservation. And yet, despite all the caution, the continent remains as mysterious as ever. There will always be things we can't study directly, environments too deep, too fragile, too interlinked with the global system to risk disturbance. Those places remind us that limits are not failures. They're boundaries that define responsibility. In respecting them, we keep the very thing we seek to understand intact. Curiosity doesn't end at the line of caution. It refines itself there, finding new ways to learn without harm. The people who work in those conditions understand that every decision is part of a legacy. Decades from now, when new technologies emerge, future scientists will inherit the record of how we treated this place. They'll see which methods preserved integrity and which crossed the line. They'll judge us not by how much we discovered, but by how much we left unbroken. That thought guides many of the choices made today. The understanding that restraint in the long view may be the greatest form of discovery. In a way, this balance between curiosity and caution mirrors the very nature of the ice itself. It moves slowly, changes carefully, adjusts to pressure instead of resisting it. It endures by knowing its limits. Perhaps that's the lesson hidden in all the layers and echoes and frozen depths, that survival, for both glaciers and humans, depends on the ability to adapt without overreaching. The ice shows us how to hold contradictions gently, to explore while protecting, to change without destruction, to move without losing form. And as the research continues, as data streams back from distant sensors and satellites, the same question remains suspended in the cold air above every camp and borehole. How much is enough? How much should we know before our knowledge begins to harm what we study? The answer changes with time, with technology, with wisdom. But the asking of the question itself, quiet, constant, humble, is what keeps the work honest. Antarctica doesn't give easy answers. It gives us silence, reflection, and the faint sound of our own restraint echoing back through the white abyss. That sound, more than any measurement, might be the truest sign that we're learning. Night in Antarctica doesn't really arrive the way it does anywhere else. It unfolds slowly, like the dimming of a world that forgets how to end the day. When the sun finally sinks below the horizon, after months of circling low, the sky doesn't darken all at once, it exhales. The light fades into pale blues, then greys, then a darkness so absolute it feels physical. The cold deepens, the air tightens, and above the horizon, the stars appear sharper than should be possible. They seem closer, more deliberate, as if distance itself has been shortened by the cold. In that darkness, the entire continent changes character. The noise of wind, the hum of machinery, the echoes of work all fade into something deeper. What remains is stillness, an enormous living stillness that fills every space between the stars and the ice. For the people stationed here through the winter, that stillness becomes a constant presence. They work under the faint glow of floodlights or the weak shimmer of auroras. The air crackles faintly with static and every sound carries farther than it should. The snow crunches like glass under boots, and even breathing feels amplified. But when the generators stop for maintenance, when everything goes quiet, the silence becomes so total that it borders on otherworldly. It's not the absence of sound, it's the complete suspension of it, as if the air itself has frozen. You can stand outside the research station surrounded by nothing but horizon and sky, and feel as though the planet has paused. There's no motion visible, no life, no signal of time, just the weight of stars above and the patient presence of ice below. That stillness isn't empty though. It's full of movement too slow to see. Beneath the frozen surface, the glaciers continue their crawl, pressing forward by centimetres each year. The hidden rivers flow, the lakes shift, the sediments settle. The earth beneath the ice remains active, breathing geothermal warmth upward in faint, steady pulses. Even in the middle of winter, when surface temperatures fall below -70, that deep motion continues. The silence is not death, it's persistence. Everything that lives or moves here does so quietly, almost invisibly. The stillness isn't the absence of life, it's the form life takes when noise would cost too much energy. Above the ice, the stars perform their own kind of motion. The air is so dry and clear that light travels without scattering, and constellations you've seen all your life appear altered, sharper, almost alien. Astronomers say there's no better place on Earth to study the cosmos. The lack of moisture means infrared telescopes can see deeper into space, detecting wavelengths that are absorbed elsewhere. The thin, stable atmosphere makes stars shimmer less, giving clarity unmatched by any observatory outside space. From the South Pole, the universe seems closer not because it's changed, but because we're seeing it through the purest lens possible, one made of air so cold and clean that it adds nothing of itself. There's a strange symmetry in that. Beneath our feet, a hidden world we can't see, and above our heads, an open one that reveals itself completely. The ice conceals, the sky reveals. Between them stands the human observer, caught between curiosity for what's below and awe for what's above. The stillness holds both directions together, the deep time of the glacier and the deep space of the stars. In that silence, the distance between past and future, between Earth and universe, seems to collapse into a single moment of awareness. It's the kind of realization that happens only here, where nothing interrupts thought except the occasional creak of shifting ice or the faint hiss of breath freezing in the air. Scientists who winter at the South Pole often describe that season as both the most isolating and the most clarifying experience of their lives. Days blur into nights, then back into days, until time becomes meaningless. The mind adapts to a world where light and darkness no longer follow familiar rules. In that state, work becomes rhythm rather than schedule. People measure progress not in hours but in data collected, instruments maintained, tasks completed before frostbite sets in. Between those moments, there's the long quiet of waiting. Waiting for transmissions, for measurements, for the slow unfolding of results that will take years to interpret. The pace of life slows to match the pace of the continent. Even thought feels deliberate, unhurried. It's as if the environment trains patience into every person who enters it. At night, when the wind subsides and the temperature drops to extremes that metal can't endure, some step outside simply to look up. There's no reason beyond the human impulse to witness something vast. The Milky Way cuts across the sky like a frozen river of light. Satellites drift silently, tracing faint paths. The auroras move above, slow waves of green and violet folding through the sky, their light reflecting faintly on the snow. Watching them feels less like seeing motion and more like watching energy think. It's not spectacle, it's presence. The atmosphere, the magnetic field, the solar wind, all interacting in real time, silent, perfect. In those moments, the stillness beneath the stars becomes more than physical. It becomes a kind of equilibrium where human thought meets planetary rhythm. That equilibrium feels fragile. You sense how easily it could be broken by a generator starting up, by a radio crackling to life, by a gust of wind carrying snow across the lights. But while it lasts, it's absolute. The body feels smaller under that much sky, the mind quieter under that much weightless brilliance. For those who live here, the experience changes how they think about the planet. The realization sets in that Earth is not a collection of separate places but a single, continuous system. The cold of Antarctica connects to the humidity of the tropics. The stillness here balances the storms elsewhere. Every weather pattern, every ocean current, every migration is part of the same loop. Standing beneath those stars, surrounded by ice that holds the memory of the entire atmosphere, the truth becomes impossible to ignore. The planet breathes as one. That awareness seeps into the work too. Scientists collecting air samples or drilling ice cores know that what they hold in their hands is more than data. It's a direct link to history. The air trapped in those crystals was once breathed by ancient forests, once warmed by different suns, once carried dust from deserts now gone. The stars above remind them that everything, even air, is borrowed. The molecules we exhale rise, travel, and eventually settle elsewhere. The atoms in our bodies were forged in stars like the ones overhead. The ice beneath holds those atoms in storage, waiting for their next cycle. The stillness of Antarctica is not just environmental, it's cosmic. It connects geological time with stellar time, reminding us that motion and stillness are part of the same continuum. Even in that grandeur, there's fragility. The ice beneath is changing, melting in places unseen. The stars above remain constant, but the world beneath them warms. The stillness we experience is temporary, a balance maintained by forces under strain. Every whisper of wind that passes over the plateau carries dust from melting coasts, a reminder that the frozen silence is part of a dynamic system responding to what we do elsewhere. The sky may look eternal, but the ground beneath it is restless. The stars bear witness as the ice begins to move faster, as the temperature inches upward, as the boundaries of the possible shift. For those living through these changes in real time, the tension between serenity and urgency defines their days. They work surrounded by beauty but driven by concern. Every measurement matters. Every echo recorded, every snow sample analysed, contributes to understanding a planet that's revealing its limits. In that sense, the stillness beneath the stars isn't just a refuge, it's a responsibility. It's the calm before decisions that affect everything. The researchers who stand on this frozen plateau know that their work may one day inform how humanity responds to its own influence. The silence they live in becomes part of a conversation that stretches across nations, decades, and generations. And yet, the beauty remains undeniable. Even with the knowledge of change, even with the weight of global consequence, there are moments of pure awe that pierce through thought, a sudden flare of light in the sky, the sound of distant ice cracking, rolling like thunder across the emptiness, the faint outline of mountains glowing under moonlight. These moments remind them why they came, to understand, to bear witness, to be part of something larger than themselves. The stillness isn't just external, it moves inward, settling in the mind as quiet clarity. Inside the research stations, where warmth and light provide small islands of comfort, people create rhythms to match the endless night. Meals become ceremonies, conversations stretch for hours, laughter fills the corridors with a fragile warmth. Outside, the temperature might kill within minutes, but inside there's life, persistence, connection. The contrast is constant. The extremes of isolation and community, of vast emptiness and close companionship. That contrast mirrors the larger balance between curiosity and caution, between exploration and restraint. The people who live here carry both within them, the urge to uncover what's hidden and the awareness of how easily it can be lost. From orbit, satellites capture images of the continent at night, a dark expanse with only a few pinpoints of light where stations operate. Those faint glows are the only signs of human presence on a landmass larger than Europe. The rest is shadow and reflection. From above, it looks like another world, untouched except for the thin halo of atmosphere shimmering at the edge of the Earth. The view underscores what everyone on the ground already feels, that Antarctica is both part of the planet and separate from it, both home and frontier. The stillness beneath the stars is not isolation, it's continuity expressed in quiet form. There's a moment, just before dawn returns after months of darkness, when the horizon begins to glow faintly. The stars fade one by one, as if retreating into the background. The temperature doesn't rise, but the light shifts, turning the snow a shade of pale gold that feels almost warm. For those who have endured the long night, it's not just sunrise, it's renewal. The world begins to move again, slowly, cautiously. The silence thins, replaced by the faint hum of activity, by radio chatter, by the rhythm of engines coming back to life. The stillness doesn't vanish, it transforms into movement. The stars yield to the sun, and the work continues. The people who have lived through that night often say that Antarctica never leaves them. When they return to the noise of cities and the clutter of everyday life, something about their sense of time remains altered. They measure things differently. They pause more often. They remember the silence not as emptiness but as presence, a kind of awareness that doesn't require sound. They speak of how, under that immense sky, surrounded by nothing but ice and starlight, they understood something fundamental, that the world doesn't need us to move for it to continue. That stillness, real stillness, is not the absence of progress, but the expression of balance. In that sense, the stillness beneath the stars is not an ending but a continuation. It's the calm acknowledgement that the mysteries beneath the glaciers will remain, that the stars above will continue to burn, and that our role is not to conquer, but to coexist. The ice will keep its secrets until it decides otherwise. The sky will keep shining regardless of whether we look up. And between them, for a brief moment in history, we stand, listening, learning, remembering what it means to share a world that moves and rests all at once. The stillness beneath the stars is not silence, it's harmony. It's the sound of balance holding for now, between curiosity and caution, between change and endurance, between what we know and what we never will. It's what the world sounds like when it remembers itself.